Right, you can hear me, right? Okay.
Yes, I can hear you.
Sure, thanks. Sure. Okay. Sure. Hello, all. Good morning. A very warm welcome to VLSI Design Conference 2023. Okay, this is Rahmatullah from Silicon Labs. I'm hosting this session today. So, VLSI Design and Embedded System Conference is a premier global conference, as you all know. So, it happens annually, and you all know that this is a special event because this is the first physical event happening post-pandemic. So, this global annual technical event that focuses on latest advancements in VLSI embedded systems is attended by many engineers, students, faculty, industry, academia, researchers, bureaucrats, and government officials. So I really appreciate and congratulate you all who took time to come over here to learn something new and to grab opportunity to meet great technical leaders here. So not taking much time of yours because we are already running out of time. So let me introduce you to the abstract what we're gonna discuss now. So as you all see our abstract, today we are gonna discuss on systematic design of bandgap voltage reference circuits. So we all know what exactly is a bandgap, how much important the reference voltage is, right? So any SOC, whatever we have currently, it definitely needs accurate bandgap for your regulators, ADCs, whatever, right? So with the technology scaling and the aging and temperature restrictions, we do definitely need to design our bandgaps in a good way. So there are different ways of designing any bandgap, be it bipolar based, be it CMOS based and all. So we're gonna discuss different types among them, especially PNP bipolar we're gonna discuss. Okay. So this tutorial will be led by our three speakers, Professor Shauri Chatterjee and Rajshekhar Nagulpalli and Mr. Rakesh Kumar. So I'm very glad to welcome Mr. Shauri Chatterjee, who has received his BTech degree in electrical engineering from IIT Madras in 2000. And subsequently, he has got his MS and PhD in electrical engineering from Columbia University, New York in 2002 and 2005. So he has become a full professor in March 2019. So currently he's also serving as Associate Dean Curriculum in IIT Delhi. So Professor Chatterjee has worked in multiple areas of power management and RF circuits. So 20 nanowatt MPPT energy harvesting design, which he has done, is still the state of art energy harvesting designs published so far. Welcome, Professor, on behalf of Silicon Labs here. So due to unforeseen situations, Rajshekhar is not able to join us physically here, but he's there in the Zoom call. Rajshekhar, you can hear us, right?
Yes, I can hear you.
Okay, great. So Rajshekhar has received his BTech degree in electrical engineering from Acharya Nagarjuna University in 2005 and his MTech degree in microelectronics from IISc Bangalore. And presently is working towards his PhD from Oxford Brookes University. Since 2014, he was with Infi, where he was involved in high-speed serial links, PLLs, and CDRs. He has also authorized for more than 20 papers in the field of SerDes and 14 granted US patents. So welcome, Rajshekhar. We also have our Dr. Rakesh Kumar Palani here, who has received his BTech degree in electrical engineering from NIT Kurukshetra in 2007 and his MSc engineering in microelectronics from IISc Bangalore. He has also his PhD from University of Minnesota in 2015. So presently he's working as associate professor in Department of Electrical Engineering in IIT Delhi. So his current interest lies in the development of IPs in AMS. So he also has served as a chair for CAS and CSS Delhi chapter for 2021 and 2022. So welcome, Professor. So we'll have the session like we have all the volunteers here sitting. If you need anything, right, we'll help you over. We'll take this session till 11 a.m., 1.5 hours. We'll take a bio break next 15 minutes. We'll resume back and we'll wind up at 12:30. Okay. So we have water, coffee machines, etc. Restrooms all marked. So we have all volunteers all around who will help you. If you have any questions, please do raise hand. We'll pass on mic. Sure. I'd like to hand over to Rakesh to start this session.
Good morning, everyone. Is it echo is okay?
Slide forward.
So this one.
This one, slide right. Sorry, slide left. This is cursor.
Okay. Okay. Good morning, everyone. Welcome to our tutorial. The tutorial will be on the systematic design of bandgap voltage reference circuits. So me with my friend Rajshekhar and with Professor Shaudi Chatterjee will be giving the tutorial. So me and Rajshekhar will cover the initial part of the bandgap voltage. We'll start with the traditional bandgap, how to design, what are the non-idealities, how people typically take care. And finally, we'll conclude with recent work done in my lab with certain advancements like a mixed mode voltage, mixed mode circuit. Then finally, Professor Shaudi Chatterjee will handle with the low power reference, basically the two transistor design, and he will take over from there. Okay.
Closer. Okay.
It's not moving. It's not moving. Okay. So the agenda for this tutorial is going to be initially we'll be talking about the performance matrices of the bandgap. Then we'll talk about MOS-based bandgap, properties of the parasitics PNP devices, principle of bandgap, chopping, auto zero, and what are the existing architectures. And we'll also talk about curvature compensation, what are the different ways of curvature compensation and what did we do. And finally, we'll give an example of how to design a bandgap. Let's say you have a spec, how will you start about designing a bandgap? How will you choose currents? How will you choose bandgap BJT sizes? And how do you do simulations and make sure that it works for any chip? How do you design startup? All those things we'll see in this present tutorial. These are certain observations what we use in the slides. For example, BGR is bandgap reference, PTAT is proportional to absolute temperature, CTAT is complementary to absolute temperature, and so on and so forth. Just for the, we'll be using these observations in our slides. So I will definitely tell you when we are using it, but these are certain observations we'll be using it. Okay, first let's see, why do you need to have a bandgap voltage reference? What is the need? We have a power supply coming to the chip. Why can't we use a power supply? Why not we just put a potential divider from the power supply and call that to be a reference? We can always do that. So the question here is a very valid question. Many people think about it. So typically what powers up the chip? You have a battery and your chip needs multiple power supplies. You may need a 1.8 volt, you need a 1 volt, you need a 5 volt for various applications. So how do you get these supplies? You get these supplies through a DC-DC converter. Okay, for example, you have a DC-DC converter which is off chip, or it can be even on chip. Let's say in this example, you take it as an off chip. And then you have a bond wire with certain very low resistance. It goes to on chip. And then you can have multiple circuits. For example, a circuit can have a current source load. And or it can have a switched resistor load, or it can be a resistive load. These are the most typical loads a circuit presents to the power network. And what will happen whenever you have switches? You will see that, like you see on the figure, you will see some spikes. You will see a lot of frequencies. You will see a lot of switching noise, and top of it, you will see a lot of thermal noise and whatever from the converter itself. That is one problem. Second problem is what is the accuracy of the DC-DC converter? Okay, let's say I want to have a DC-DC converter, which will give 1 volt. It may give 1 volt plus minus, let's say 5%, 10%. You'll always have a spec. No DC-DC converter, no circuit give an exact 1 volt. And that plus minus 10% is a function
Still
of.
they are not able to hear. Yeah. Is it okay now? Is it okay now? Can you hear me now? Okay. Okay, that's fine. So the output of the DC-DC converter, if you, is it okay? Okay. It need not be 1 volt. It can be plus minus 5%. It can be plus minus 10%. That is one problem. Second problem is this percentage depends on the temperature. When the temperature changes, you may get 1.05 volt. At minus 40, you may get 1 volt. At 27, you may get 0.95 volt. It's all possible. And top of it, the voltage also depends on how much current you draw from the DC-DC converter. No DC-DC converter has an output impedance of 0. It has a finite output impedance, so that voltage keeps on fluctuating. So what? So you're not going to get a proper reference voltage on chip if you tap from VDD. The reference voltage itself will have a plus minus 10% variation. So why this is a problem? What is the problem if the reference varies 10%? Let's say. Answer to that is these reference voltages are given to, let's say it is given to ADC or a DAC to convert a dimension quantity to a dimensionless quantity. It's to analog to digital. Let's take an example. Now you have an analog voltage, you compare with a reference, you give a digital quantity. So whatever you give on the digital output, it depends on the reference. Now if you add some noise or if the reference voltage is uncertain, whatever you're going to get on the digital is going to be cranky. So this is not good, and this gives a lot of errors. So that's a need. You need to have an on-chip, clean on-chip reference voltage, which is stable over temperature, which is stable over power supply, and also we are not going to draw any current from that reference. Okay, we are going to use that as a reference voltage, so it will be stable. Okay. And the second point is noise, like we discussed. So if you have a noise on the reference, no matter what we do, let's give the reference to an ADC or a DAC. It's going to affect the SNR of the block directly without, it's going to affect directly. Whatever noise on the reference comes out directly, no matter how clean you design the ADC. You may have a wonderful 16-bit ADC. It can be Delta Sigma ADC or whatever your choice. But if the reference is crappy, output is crappy, no matter what you do. So the noise affects directly. Second is if you think of VCO, we talk about jitter. I know we are right now in the era of designing a sub 100 femtoseconds jitter is a pain. We are going that era. If you have a noise on the VCO, it affects the phase noise and it affects the jitter. So for all these things, we need to have a clean reference. So point A is that we need to have a stable reference. Second is that we need to have a clean reference. Like that, the noise on the band gap should be extremely low. That depends on the spec. And third is byproduct, like we need to have a bias current to major blocks, like you're designing operation amplifiers, you're designing TIAs, you're designing whatever. So in order to maintain the UGB constant, you tend to maintain the transconductance of the operation amplifier constant. So you need to have a p-type current. It will be nice if the band gap itself gives a p-type current. It's not a must, but it will be a nice phenomenon to have the one circuit which can give a constant voltage. And also it gives a p-type current to maintain the GM of the circuits to be constant. Okay. So for example, if you're designing a VCO, you need to have a startup margin where the startup is GM RP is a loop gain. You want to keep like 6 dB for the proper startup. So across temperature, GM will change. So if you pump a p-type current into your VCO, most likely your startup margin will pretty much will remain the same across the temperature range. For that, you need to have a p-type current. Any questions on this? That's the reason you need to have a band gap. Anything on any questions on this? Whatever. Okay, and where band gap voltage reference is used. Okay, we are all talking about band gap. What are the locations it is used? For example, you see a transceiver block diagram on the top, where you have a LNA, you have a mixer, and you have a demodulation. Then it goes to baseband, and finally it goes to an ADC. That's on the receiver side. Bottom is the transmitter side. Again, you give a digital signal, you up convert using a mixer, and finally you transmit using a DAC. Now, for example, where I showed on the blue curve,
So for an ADC, for example, you need to convert an analog to a dimensionless quantity. Okay, it's a digital. So for that, when you convert an voltage, you have to have a reference in voltage. So you need a reference. Or you take a current, you convert it a current reference. Again, you need a reference. So that need to be clean. You need to have a band gap there. Same thing applies to a DAC. And for example, same thing happens in the local oscillator. We need to have a bias current. And every subblocks also need a bias current. So pretty much everywhere you need to have a bias currents and voltages. So you need to have one band gap reference voltage. And then you will have a master bias which will generate the currents to various blocks. Okay. So that's why this is necessary, and this is important. This was important. This is important. This will be important in future chips, and you can't get away without designing a band gap. Okay. Okay. Fine. We want to develop. We want to produce a voltage which is independent of temperature. Okay. So what is the basic idea? The idea is very simple. Let's somehow find a voltage which drops with temperature. We call that to be a CTAT. Right? And also let's find out a voltage which increases with temperature. We call that to a PTAT. And then what you do is that you just average and weight and add it. Okay, VBG you can add to be CTAT voltage plus some constant into a PTAT voltage. In the bottom curve, you can see that red color is a CTAT curve. It drops with temperature. Green is a PTAT, which increases with temperature, and you get a blue if you add appropriately. Okay, this is a basic idea of the band gap. Now the question is like, okay, all good. From where are you going to get the CTAT voltage, and then where are you going to get the PTAT voltage? Okay, so if you take a diode, okay, I will say why I put a BJT. Ideally, it can be a diode. If you take a diode now, and if you look at the collector current, it's nothing but IS into e power VB by UT. UT is a thermal voltage. So that's what the device physics people have modeled it for the diode. And from there, you can see that VB is nothing but KT by Q into ln of IC by IS. Yeah, it looks wonderful. You see that VB is proportional to temperature. So it looks like VB should increase with temperature, but it doesn't. Why? The reason is IS also increases with temperature. IS is a saturation current for the bipolar that increases with temperature with an equation IS equal to I naught into e power minus VG naught by UT. VG naught is the band gap of a silicon, band gap of that material. It need not to be a silicon, band gap of the material. Now you go and plug this back and you remove all the non-linear terms. You get like VBE is nothing but VG naught minus KT by Q into ln I naught by IC. Okay, I naught is a constant, IC is a constant. So ln I naught by IC is also a constant. You see that VBE becomes a CTAT voltage. It has a negative temperature coefficient. At 0 Kelvin, you see a band gap of silicon, a band gap of the material, and after that it keeps rolling down with temperature. On the right hand side, you see that for the different material, top is a gallium arsenide, mid is a silicon, and bottom is a germanium. All exhibit the similar nature. It has a curvature because we are ignoring the nonlinear terms. We extrapolate, you will see that for the silicon, at least you get 1.205 electron volt, and so your voltage should be 1.2 volt. Okay, so this is what is the behavior of the diode. Okay, now we know that how to generate a CTAT voltage. We'll see some more interesting on this. Okay, so we saw that VB exhibits a negative temperature coefficient, and initially I told that we are going to ignore the higher order terms. Now you can ask me what are the higher order terms and what is how does it value to ignore the higher order terms? In order to explain that, we will see that your IC is proportional to IS into some exponential VB by UT, and IS is proportional to mobility into temperature into Ni square. Now, if you look at mobility, it decreases due to with temperature and due to higher collisions, and the coefficient is T power minus 2 by 3. And similarly, intrinsic concentration is a positive temperature coefficient. When you keep increasing the temperature, the number of carriers increases, and reverse saturation current also increases exponentially. Okay, according to these equations, which I'm not dealing with, I just took some references. So from that, you see that in the first order approximation, you will see that it's a straight line. Okay, that's what we saw. You get 1.2. Now you say that, hey, look, why are you approximating as a first line? We want to do a second order approximation. If you do a second order thing, you will see that VBE is nothing but VT into some linear term, and then you get a second order term. This long term is responsible for curvature. We will see how to clean up the curvature in future slides. And again, you can go with the third order approximation and henceforth by having this polynomial expansion, bg0 minus bt minus et square, and b and c are some constants. An actual curve is shown in the green, like you saw in the measurement results of gallium arsenide, silicon, and germanium, what is showed in the figure. And now you draw a tangent and it will go and extrapolate at 1.2. Okay, this is the CTAT. How do you generate PTAT now? We know how to generate CTAT. It's very easy. Okay, you take a current, you put into a diode, you get a CTAT voltage. Okay, it's all good. So now the argument to that is like, hey, look, I want to generate a PTAT voltage. What I do is, now let's say that I take a current, I put into a diode of certain width. Now I take the same current, I put into another diode of a higher width. What do you think will happen? The voltage developed across the diode of a higher width will be lower, because that will offer a lower impedance and that will be lower, and this guy will be higher. So if you take the difference, it looks like it's going to be PTAT. You'll see by mathematics, but it can be PTAT. So now there are various combinations what one can use for optimization of the band gap. One way is like, hey, look, I will generate a PTAT by taking the current and putting it into two emitters of two different sizes. 1:n as I see here on this. Or I will say that no, my BJTs I will keep to be same. I will take the band gap of the same, I will take two identical band gaps, but I will put two different currents. Okay, I will take I1 and IC1 and IC2. Or I will do both. Okay, I'll put two different currents and also I will size the BJTs differently. Okay, these are the three ways you can generate PTAT voltages. And sizing of the BJT is chosen to be the most prominent one, simply because if you choose currents, the resistors, what is involved in generating of the PTAT tends to become big, and hence the area tends to be bulky. So typically, I have not seen people going into the approach of scaling the currents, unlike scaling of BJT diodes, simply because the resistors tends to be really big. Once the resistors are big, the leakage current with leakage current and water non-idealities, you get a lot more errors. Okay. And I have seen some work where they put 1:m and maybe use to 1:2 current. The current maybe 1:2 you can have, not more than that. But if you look at the idea is the same. You need to just look for the current density. Okay. Now another way is, hey, look, why not I generate a PTAT using MOSFET? Yes. In ISSAC 2009, it has been done by Twente University in Netherlands. So what they did was they took two BJTs, two MOSFETs, they put in subthreshold region. The moment you put in subthreshold region, current flows in the center of the device. It doesn't flow at the surface. It looks very close to the current equations becomes very close to a BJT equations. And then you take the VGS1 minus VGS2. Apparently, you will see that it gets a PTAT slope. Only difference between this PTAT slope compared to the one what you obtain with using BJT is that you get an eta, and hence you get a typically higher PTAT slope compared to a BJT one. And since you take the difference between the two VGS, VT is gone, so you don't have process corners anymore. Okay, it may be SSFF or whatever it is, you don't have it. And people use this also for generating PTAT. Okay, this is another popular way of generating a PTAT. No need to do with BJTs, you can also do with MOSFETs. Now you have a PTAT, you have a CTAT. The next step is you take the PTAT, you go and amplify, you add to the CTAT voltage. Okay, and you get the ideal constant voltages. So you take the diode voltage, that is the CTAT, you get a delta VBE, that is PTAT. You amplify by a factor of alpha, then you get VBE plus alpha times delta VBE. So right hand side also is shown clearly. You get 1.2, VBE is the CTAT, PTAT is alpha times delta VBE. You add it, you get the reference voltage. That's a basic idea. Now, yeah, it's all good mathematically. How do you design a circuit to do this? You need to design a circuit which can take a CTAT, and we should generate a PTAT. Then it should also amplify the PTAT voltage, and then we should add to the CTAT voltage to give constant reference voltage. Okay. For that, initially the first circuit what people developed in Bandgap is Brokow. It's very similar to the core is very similar to what we have. You have a NPN. Let's say that in a technology you get an NPN diodes. Okay, during that era we do have it was all by CMOS process, BJT process. We had a NPN transistors. So the idea is that like, hey, look, I put a lower current density. VB1, which is higher. Inside VB1, I put a resistor and VB2, and I size the BJT m times. And then the voltage developed across a resistor is nothing but VB1 minus VB2 by KVL. And hence the current has to be PTAT. And then when the current is a PTAT, the same current is mirrored into the other BJT at the top. Now the current in R2 is also a PTAT. So you can see that VBG is nothing but some CTAT plus some PTAT, you can add it. And you can get a constant voltage at the base of the NPN. Okay, this is one way of generating the bandgap voltage. This is the familiar block-off. A modified block-off is nothing but you don't have a diode, you put an operation amplifier to make sure that you don't have the current mismatches. Okay. So a couple of issues with this architecture is that you can have the VDS mismatch due to the current mirrors, and hence you get some inaccuracies. The second problem what you're going to have is that like these BJTs is going to take base current, and the moment it starts taking base current, definitely the right hand side current is going to be different from the left hand side current due to the base current, and hence the beta dependency will be there. So if you derive it, we'll see that the bandgap voltage will be proportional to beta. So that's a real pain for the circuit. Okay. So now let's move on and say that, hey, look, we can design a bandgap using BJTs. We can design using NPN. So why not we stop it there? What are we even doing it? It works. When we moved to CMOS era, then we saw that, hey, look, diodes are not available. We don't have any more diodes simply because the P substrate is grounded and you have an N well. So it's only possible that, let's say that you want to take a PN diode from P plus and N, the bottom P is already grounded. So you cannot have a diode, you can have only the BJT. There's no way we can have a diode with nothing connected around it. So then we saw that, hey, look, at least we can use a BJT, and that's why we are using BJT. And only BJT available was PNP. Okay, it's a vertical PNP. It's a parasitic BJT. Nothing with a poor beta. Beta is about like 1 or 2. And maybe we can use this for developing voltage references. And if you have a triple well process, then yes, you will have a NPN transistors. I think from 65 nanometer onwards, we do have an NPN, but still most of the band gaps I see even today are with PNP only. For the simple reason is, even if you have an NPN, you're not going to have only NPN, you're going to have NP. You're going to have a thyristor. So that's why that NPN is not used even in lower technologies. We'll still stick with the PNP for developing any band gap voltages. Okay. Now, how do you let's say that you want to generate a band gap with your diodes. So you don't have 3 terminals available, you have only 2 terminals available. 1 terminal is already grounded. Yeah. What is that? No, the problem is that bottom P substrate is already grounded. Again, you will have an N well to be connected to VDD. All the P substrate is always grounded. So you don't have an isolated PN. So let's say you have PN, and after the N you can have a P or N plus, right? That is either connected to ground or VDD. You will have a parasitic some structure next to that.
So even in the triple well process,
you don't have diodes. Yes, there will be some current flowing from that into P substrate. It can be low, but you have some parasitic device. So you don't have PN. That's all I'm saying. You don't have an isolated PN. Let me put that way. You don't have an isolated PN like you have an off-shelf diode. You'll have something connected to that. Not sure. Again, there, I'm not sure. Even in SOI, right? You can have N plus, P, N plus. Bottom, I agree. You are putting a cap and isolating the substrate, but you'll have N plus, P, and N plus. Beside this N plus, something will be there. If you are going to take a horizontal direction also, if you take an NMOS, it's N plus, P, and N plus. After the N plus, there will be something. In that also it will be something. Unless until you say that, hey, look, I put an oxide here, I put an oxide here, cut it off, I put a P and N. That's going to be a lot of steps, and I don't think people will be doing it. It's possible with the shallow isolation, but I don't know. I don't think people have done it So
just do a plus inside P sub.
what is it?
Just a plus inside P sub.
Okay, you have N plus, you have P sub. You'll have some other transistors there, right?
Yeah.
Then you'll have a parasitic with that. So you can't have a diode, basically. That's a problem. Any more question on this? Okay. So clearly one terminal is always grounded. So you have access only to 2 terminals of the BJT. That's a problem. Just for simplicity, I retained with an NPN. You can always replace with the same thing with the PNP in the slides. With one terminal is always grounded. Okay, the analysis remains the same. Okay. Now the argument is with that, how to generate bandgap reference. So your aim is to generate a CTAT, which is a VBE1, and develop a PTAT, which is VBE1 minus VBE2, and multiply that with a scaling factor alpha. That is the aim. Somehow we have to generate that. So just rewriting it, we'll see that VBE1 into 1 plus alpha minus alpha into VBE2. Just reframing the equation. VBE1 is a voltage across a diode of a higher current density. VBE2 is a voltage across diode of the lower current density. Okay. Now, how to amplify VBE1 by 1 plus alpha? It's very simple. You take an operation amplifier, put a non-inverting configuration. VBE1 output will be VBE1 into 1 plus alpha. And how to develop, amplify VBE2 with minus alpha? Same argument. You take VBE2, put an inverting amplifier, it goes to minus alpha into VBE2. Just use superposition. Once you superposition, you'll get like VBE1, VBE2 connected. You put an operation amplifier, you're done. Okay. Okay, all fine. How are you going to generate VBE1 and VBE2? You need to have some current flowing into a diode, right? Yeah, there can be some current flowing in VBE2, but it looks like VBE1 doesn't have any current. So you just connect the same resistor, alpha R, to the output. That also sinks the same current. VBE2 also takes the same current. Just redraw it, okay, so that is human readable. You take it, you read it, you'll see that you take the current VB1, VB2. That R is the one which is a resistor which converts the PTAT voltage to current, and it gets amplified by alpha R to get VBG. Okay, these are most commonly used bandgap architecture. For simplicity, I drawn NPN, but it can be PNP diode. It's not a problem with 1:1. I just retain the same convention. Okay, this is the high voltage bandgap used for a lot of era and many chips and silicons. And this is a very popular one. And more or less, every architecture you see on the bandgap has a bandgap core. This is also called to a bandgap core, and we use that only. Okay. Yes, I'll talk about that. And when I'll show you a circuit how to bias operation amplifier. In order to answer you, what you do is that you get this current, right? You take the current and mirror back into the operation amplifier. So that is a bias current. There's nothing available, only VDD. You take the same current and pump back into operation amplifier for this operation. The advantage that gives is like all the VGS on the operation amplifier tracks because it has the same current, and that also helps you to give a low systematic offset. I will cover that also. Yes. No, we need to have a startup. We have slides. I will show that also. There are certain issues with this architecture, and there are ways of solving it. I will talk about that. Okay, the first and foremost question is, hey, look, there's an operation amplifier. How do you find operation amplifier polarity? Okay, I explained how did you derive the circuit. From that, it's very easy to say that, okay, there's an inverting configuration, there's a non-inverting. You go ahead. Now, if I just show you this circuit on the left-hand side, why should that has to be negative, why that should be positive? It can be opposite. How do you find the operation amplifier polarity? Sometimes it becomes a little tricky if you go with loop gains. Okay, let's say I go around the loop with positive feedback loop gain, negative feedback loop gain. It's become a little tricky, little painful. On the other hand, it's very easy if you go with this intuitive graphical analysis. Now, the operation amplifier will try to make the voltage on the first diode to be equal to the voltage plus resistor on the second diode. Okay, call that to be Vx. So that's why I shorted it and called that to be Vx. And on the ID is that current going into the diode that has an exponential nature. So that is a red curve what we show here. IR is a green color curve that has an exponential which is degenerated with a resistor. So that's why that curve goes here. And it has two stable points. Wherever the two currents are equal, it's a stable point. For now, let's ignore the 0, 0. Okay, let's say that we have a startup circuit to kick the circuit out of the startup into the operating region. Now the question is like, how did we go to P2? Okay, P2 is a correct operating point. At any point, Vx is the same. So you can draw a vertical line and see. Let's say that somehow it moved to P1. At P1, you will see that ID is lower than IR. So what it will do, it will start increasing the current. Once it starts increasing the current, so ID will increase, IR also will slightly increase so that it reaches the correct operating point. Okay. So this method becomes easier for us to analyze in order to find the polarity compared to going around the loop gain. And this I found to be useful, especially if you are dealing with a complicated bandgap architectures of finding the polarity. Okay. There are few issues. I know we are just for time conservations, we are noted for few issues of bandgap. Again, there are multiple issues, which we are not going to talk in detail of today. Like if you go for chopping, there are multiple issues on chopping. We are not going to address everything and say that, okay, these are ways of solving it. But there are few issues like startup, like someone pointed out. At zero current, both the diode voltages are equal. You have a stable operating point. It need not to be a zero current. It can have a multiple operating points too. There are architectures where you can have 1,000 operating points. Your circuit should be kicked off from that and go to the stable operating point. The second is operation amplifier. It can have an offset. It can have flicker noise, and that sees a PTAT gain when you refer to the bandgap output. That can be a pain in itself, because offset has two varieties. We'll talk about this. One is systematic, one is random. And the way you deal with the systematic offset is different compared to the random offset, and that has certain trade-off. And third is a current mismatches in the diodes. You saw two PMOSs that have a VT and beta mismatches that can give some errors. And then finally you have a beta mismatch between the diodes. Okay, we'll talk about only 4 issues. There are multiple issues, as I pointed out. We are not going to deal in this tutorial. So the first is the startup. Now, the argument here is that, like, now let's say that during startup, I1 and I2 rises from 0. Finally, it reaches a desired PTAT current. Okay, that is a aim. But let's say that I2 is less than I1 initially because of the resistor. So, and hence, because of the resistor, you have a low voltage drop across R. And hence, after the desired operating point, you will see that voltage drop across the resistor is high. At the desired operating point, you will see I1 equal to I2. Okay. So this is what we will be using for designing the startup circuit. And hence, we need the aim is that somehow we need to push the circuit out of the undesired operating point at 0 current. Okay. We just use this intuition in order to design the startup circuit. Okay. And the requirements of the startup should be that after designing the startup, there should be only one desired operating point on for the reference circuit. You can't have multiple. And you can't have any conditions on the supply ramps. Your supply can come up with whatever ramp rate it needs, but your bandgap should come up. And there should not be any dependency on the leakage current. And the startup circuit should be disabled after the BGR starts up. Okay, once the startup bandgap reference starts up, your startup circuit should be disabled. And it should be able to come back again if the bandgap goes into the 0-0 condition. It can also go at any point of time. Then the startup circuit should kick in, and again it should put in the correct operating region. And it should not oscillate. And please remember that any startup circuit, however they move, is a positive feedback network. Okay. Any startup, however you do, is a positive feedback. So if you're going to give a strong kick on the startup network, it's going to oscillate.
You said we shouldn't oscillate, right?
Yes.
Are there some things we need to take care? Because sometime back when I designed some circuit, by default there was a feedback, and it was designing a gigahertz clock without we knowing it. It was this. It took the feedback and it was giving a gigahertz clock. Okay.
So the way you need to design for the startup is it has a positive feedback. Once the circuit starts up, you need to make sure that gain of the positive feedback becomes 0. That's only possible when you disable that block. Let's say that when the bandgap starts up, somehow you make sure that current in that starting branch is 0. If you ensure that the gain on that network becomes 0, and hence it will be stable. So that you need to ensure across Monte Carlo, across corners. That's a real thing. Because I have seen when I design some circuits, it all worked. So typically the way we check the stability is by giving a sharp kick. You give 1 ampere kick on the high impedance node. So you put the circuit to either VDD or ground and see how it comes back. And I see that at some corners, you see a sustained oscillations, even though my phase margin, gain margin, or the bandgap loop is fine. And when I disable the startup circuit, then it was all fine. And I found that at that corner, maybe some leakage current is going into the startup node, and that kicked out to the oscillations. So this is something what you need to watch out for. So you have the startup circuit, you give a sharp kick, give a 1 ampere current, impulse current at high impedance node and see what happens. If it oscillates, then watch out for it. I'll show you. I have that also. How to verify the startup also I have. We'll skip on this for now. So now we just use a pre-touch cell to think about the startup. Now you have two currents. One is on the diode, one is on the diode with the resistor. You see that your two nodes, 0 current, and the green is a stable operating point. And typically the way it goes from the 0 to the real operating point is the strategy trajectory shown in the right hand side of the curve. So you hit a voltage, again it goes to the other voltage and it goes like that. Okay, I'm not going into details on this. Okay, the first argument is, hey, look, I want to design a startup. Why not I rely on the leakage? Because all transistors have leakages. Okay, why can't I say that, okay, there'll be some small amount of leakages will go into a particular node, which will make sure that it doesn't give a 0 state. Like in VCO, VCO rely on a noise, right, to start up. Why not I do the same thing for the bandgap? It's a bad idea. The reason is like, the leakage depends on temperature. Let's say your bandgap doesn't start at -40. Your leakage is also very small. It's not going to start up. Second is that how do you know that only particular polarity of the leakage will be there? Your PMOS will have a leakage. Your BJT will also have a leakage. So the net effect may be that it will never make the bandgap to start up. That's also possible. Okay. And third is that like modeling of the leakages, I don't know about in these technologies, I don't know how accurate it is. So I've seen orders of magnitude of at least 10x. You say that simulation leakage is 1 picoampere, in reality it may be 10 picoampere. It's possible. So don't do this. Okay. Basic idea is that don't do this. Don't rely on leakages for startup. You design a startup by yourself. Second question is like, why not I give do a startup with the power transient? Let's say I have a capacitor CR circuit to detect the transient. When the power ramps, your gate of this PMOS also changes, which will just pull that network down, and then the bandgap starts. I can do this, right? Why not I do this? Yeah, this is a good idea, in the sense that this will only work when you give a power ramp. Now, let's say that your power is ramped and VDD is constant. After that, something happens and bandgap goes to the 0 current. What will happen? The circuit will not even respond. So, not a good idea to do this. One more bad idea is don't have a low impedance node. I've seen something like this where people use source followers to inject some current into the BJT and then say that, okay, fine, when the voltage increases, the source follower will be cut off and you are all fine. But again, this is not a good idea because it's a low impedance node. You can't have two voltage sources in parallel. Simple. Diode is also low voltage, source follower is also low voltage. Okay, although you cannot have a 0 current, you'll have some current going into the source follower, and that will actually give a lot of errors. So this is one of the circuit what I saw in industries. People use it, but it's not a good idea because it gives errors. Okay, not a good idea. Then how do you design a startup? There are a lot of startup circuits available in literature. Okay, lot. So all of the startup circuits work in the same phenomena. You need to have a sensing circuit which will detect the 0 state. Now somehow you have to detect 0 current. Whenever the current in the bandgap core is 0, you push some current into the diode. Whenever there's a current in the bandgap core, you cut off the startup circuit. That's all. So for example, in this startup circuit, what I have here is that like, hey, look, I took the P-tail node, connect to MSP, connect to RS. When the current is 0, voltage across RS is 0 because there's no current in MSP. So the inverter output will be 1, which will turn on the NMOS. So it will pull the P-tail node down. The moment it starts pulling the P-tail node down, there will be voltage developed across RS. When the voltage is sufficient to turn more than the trip point of the NMOS, then that NMOS will be off and P-tail will remain as it is dictated by the operation amplifier. One of the commonly used startup circuit is this. And typically the inverter, what I showed here is an aesthetic inverter. Don't put a regular inverter. Put an aesthetic inverter so that you have that margin. Okay. Now answering to your question, how do you simulate a startup? Yeah, I designed a startup. How do you know it is valid? How do you know that it will be robust? Why is detecting startup issues is difficult, and we need to run a lot of simulations. And how can you be sure that there's only 1 0 for point and a reset point. There's only one operating point after the startup. How do you make sure that it is fine? These are the questions what we need to answer with simulations. We need to prove it and say that, yeah, it works. The reason is like many bandgaps fail due to startup. And startup failure can occur at any particular PVT condition. There are so many corners, so we don't know. Sometimes simulations cannot even catch at a particular supply ramp rate and leakage current, and if you have some initial voltages and the capacitors, and maybe even due to some parasitic capacity coupling. So the idea is very simple. Now let's say that you attach a voltage source. This is a DC. We have checking the startup. You attach a voltage source to a particular any node in the network. It can be any node. For example, here I attach to the P-tail. Now what I do is I sweep the voltage from 0 to VDD, ground to the maximum voltage. Now let's say that the circuit has 5 startup points, 5 stable points. At every stable point, your P-tail will be stable and the voltage source also will have that particular voltage, right? So the current will be 0. There will not be any current from the voltage source at every stable operating point. So what you do is you just monitor the current from the voltage source and see that how many zero crossings it has. It has so many stable operating points. Okay, just sweep it from 0 to VDD, look at the current, look at the zero crossings. Number of zero crossings gives the number of stable operating point. And this experiment you repeat across 1000 Monte Carlo at least, and across all corners, and see the zero crossings. Also observe how close is to the zero crossings. For example, in this curve, you will see that there is a zero crossing and there's some current, there's a peak near the zero crossings. You can also go and cut the zero crossings. Look at that margin. And you quantify by your design skills and experience, saying that this is good enough or not, and say that this is fine. Okay, this is how you simulate the startup circuit and make sure that this is stable. And I would prefer at least take 1000, because we have seen occasions where the 997 runs are fine, and we'll see that out of 1000 only 1 run failed, startup failed. Okay, the startup occurs due to bandgap and also due to self bias, which I'll talk later. What is that? Yeah. No, it's a DC. It's DC. DC sweep. Just give a DC sweep and look at the zero crossings. No, power amp is fine. I'm not talking power amp here. So here we are only talking, saying that, okay, look, VDD is constant. Now, if the bandgap has any other stable operating point, the current from the voltage source will be 0. So that's all we are talking here.
We need to check the startup condition and that condition.
Correct. This you are checking for the DC. That's all. What you're saying is true. No, here Vtest will be equal to P-tail. In this circuit, Vtest, whenever Vtest is equal to P-tail, the current will be 0. Correct.
If there are multiple points, that means there are multiple
Zero cross. Correct. That's all. The idea is very simple. Yeah. I didn't follow what you're saying. Yes. Yes.
That is only point.
No. It can also go into the diode, right?
Because those are hybrid.
No. It can go into the diode, right? No, from Vtest, if any current goes, okay, that is fine. No problem. The problem is that if the Vtest, there's no current is going, that is a failure point. Because only then you will say that Vtest equal to P-tail. That is a point, there will be 0 current. So that means that is a stable operating point. So you should have only one zero crossing. Okay. It's hard to answer, but my guess would be that maybe you are not disabling the startup. When the bandgap turns on completely, your startup should be turned off. If that is not happening, then something, what you're saying, can happen. Or I need to check. before answering. I don't know. It's hard to answer, but I don't know. It can be. So the way when I design the bandgap I have is that I'll also have a test port to disable the startup. For example, in this case, I will just connect the NMOS to 0 when I want to disable the startup, just for checking those conditions. Let's say when the chip comes back, it starts oscillating or something like that. I will take that NMOS gate and put into 0 forcefully to see what happens. If you have that, it's easier. Otherwise it's hard. It can be even due to systematic offset, or it can be due to the operation amplifier. There's a number of things can happen for the things what you're pointing out. But typically it should not be a time variant thing like you're pointing. Like when every time you switch on something is happening, it's hard for me to predict, but I don't know. I have to see. Okay. The next is that like operation amplifier offset. Okay. So operation amplifier offset, the idea is that like if you let's say that the operation amplifier has an offset VOFF. Now for all our analysis, we'll say that VB1 is not changing. That offset appears across the resistor. So it generates a current. If you refer to VBG output, you'll get 1 plus alpha into V offset. Very simple. So that is a big pain. For every doubling of offset, we need to increase the size of the transistors by 4x. If you want to reduce the offset from 1 milli to 0.5 milli, the transistor sizes should go 4x. Now let's say that you see it also has a gain of 8. You are dead. Okay, it's not possible to increase the sizes. So that's a problem. And the offset itself can be two things. It can be random offset. It can be systematic offset. Okay, random offset, yes, you can do something like chopping or auto zero to take care of it. But systematic offset, you have to live with whatever. There's no other technique apart from matching. I'll show how people do that. Okay. Now first let's try to understand what is systematic, what is random. Systematic offset is nothing but mismatch in the circuit because of the poor design. It comes from the designers. Okay. If you are a poor designer, you'll have a lot of systematic offset. A good designer will try to match the current densities and keep the VGS and VDS of the transistors of all the critical transistors identical. So the systematic offset becomes very low. And it can be verified using SPICE simulations. Okay. Random offset, it comes due to a number of parameters. It comes due to fabrication. Every different chips can have different values. Mean will be the same, but it can have standard deviation around it. That is random variations. That is viewable using DC match and Monte Carlo simulations. Okay. So how do you handle systematic offset? For example, so like you pointed out how to design the operation amplifier, the circuit of operation amplifier shown here. All the green PMOSs, all the red are NMOSs. So what we do is match the current densities of all the PMOSs. Okay. If you match the current densities of all the PMOSs, one can say that VGS of M1 should be equal to VGS of M2, should be equal to VGS of M3, should be equal to VGS of M4, should be equal to VGS of M5. Okay. Because all the current densities are matched. When all the current densities are matched, PT will be equal to P tail, no matter what you do. When PT equal to P tail, what is the input referred offset you are going to have? The input referred offset is going to be PT minus P tail divided by the gain of the first stage. So ideally we match PT equal to P tail. So when input referred is going to be very small. Typically, if you do this, your input referred offset will be something about 50 microvolt or less than 50 microvolt you can achieve. When you're designing sub 1 volt, 10 to 20 microvolt is easy to achieve. It's if you put little more effort, 10 to 20 microvolt of an input referred systematic offset you can get. Okay. And top of it, what you do is you do a self bias. You take the current, put into M5, measure to bottom NMOS and measure it back and take it out. Okay. So what we see is if you do a self bias loop, it increases the DC gain. So one can extend the self bias. This is our TCAS2. What you do is you sense the P tail, you sense PT also. Again, you make sure that PT and P tail, make sure that is equal by the loop for M5 and M8. M5 and M8 loop will make sure that PT equal to P tail with a one stage gain. Again, when you input reference, it will be very, very small. Okay, this gives you less than 10 microvolt of systematic offset. Now, one should make sure that this self bias loop is also a kind of a positive feedback, or you can call that way. It's hard to debate positive and negative feedback, but you have to kill the loop gain. So put a big RC port to kill that loop. Otherwise, it oscillates. This is one neat way of reducing the systematic offset. And you can see that with the self bias, your DC gain has gone from 56 to 90 dB. And you know that if you increase the DC gain, you can also reduce all the offsets. That's the mechanism it happens. Indirectly, it increases the DC gain with that another loop without affecting the loop dynamics. So if you want to design an operation amplifier with a higher UGB and higher DC gain. This is one technique what anyone can use. Put a self bias for increasing the DC gain, pump more current in the first stage to get the UGB, you get both. Okay.
Sorry to disturb you guys, but if you need any coffee or tea, please do have it. Because break is just 15 minutes, right? We may not be able to accommodate all. So if anybody would like to, please do have.
Sorry, this slide is slightly messed up. Okay, here the idea is to show that the threshold voltage is a Gaussian with mean of sigma, mean and certain sigma. It's the figure is just missing up. I don't go over it. Okay. So here again you have a current mismatch beta, where you say that it's always given in percentage. Yeah, A beta by square root WL. One thing what is a takeaway from this mismatch is beta mismatch is independent of process, whereas a VT mismatch is a function of process. However, VT mismatch will result in a current mismatch, which is independent of temperature. The tempo is 0 if you are limited only with the VT mismatch. However, if you are limited with the beta mismatch, you do have a tempo. For example, in the band gap, where you don't care for the absolute voltage, but you care for the tempo, you really don't care for the VT mismatch. You care for the beta mismatch more than VT mismatch. So this is the takeaway what I want to show with the slides. Sorry, something messed up with that formatting.
But how do we predict VT mismatch? I mean, we need to foresee how process variations will be there.
Again, through simulations. It's Monte Carlo. Okay. So these are the mismatch sources you get in a band gap. Resistors typically give 1%. It's pretty good match. We use resistors for building ADCs. So we get a good matching in resistors, at least these technologies. No need to worry much. BJTs give 0.4% mismatch approximately. Again, mass current mismatches. These are percentage error you will get. Delta beta by beta the whole square plus GM by IB into delta beta the whole square. And then you're going to have the operation amplifier offset. Random source and operation amplifier offset. Okay, I'll go with that first. Correct. So now let's say that you have a random mismatch on the operation amplifier. As I explained, you will get the amplifier, you will get the amplification by P K. That's what is shown in the red curve, R2 by R1 in VOS. VOS can be trimmed with temperature, but the tempo of the VOS will kill you. Okay, the tempo of the VOS will come from the differential pair offset plus the load offset when you input refer it. Typically, the tempo of the load pair is what which kills you more than the differential pair itself. And how to solve it? You do chopping. That's what many people do chopping. I think we have certain, I not put in the slides in our group, we develop certain band gaps which doesn't use chopping and still get a very good response for the offset. Chopping is a known phenomena for the edges, just a brush up. So what you do is that in the chopping, you take the signal, you go to high frequency, you process it, you bring back to the DC. In the process, what happens is only the offset and flicker noise goes to the high frequency, it doesn't come back to DC, you go filter it off. So you remove the offset by that. As shown here, the signal here goes to a higher frequency, but offset will stay as a low frequency. And the final mixer, offset goes to the higher frequency, your signal comes back to the baseband, and then you filter the offset off and you are clean with the offset and flicker noise. So what is the problem with this? So the way you do chopping is that you cannot do chopping on high impedance nodes. Couple of takeaway: don't do chopping in high impedance nodes. Always do chopping in the low impedance nodes. Otherwise, you'll be affecting the DC gate. Okay. For example, you put a folder cascade. You do chopping on the low impedance nodes, on the PMOS sources, and the NMOS sources. Don't do the output. Okay, it's a pain. Second is that some people put the notch filter inside the loop to clean up the notches, to clean up the swing. And some people will say that let you get the swing and you clean up at the outside. It has few advantages and disadvantages. Like for example, if you're going to put the notch filter outside, you need to accommodate the swing inside the operation amplifier. The problem is that the operation amplifier swings with the non-linearity of the operation amplifier, you will see you get some DC component and that sees a P-type gain. It can't be completely eliminated. Now you put the notch filter inside the loop, you can't get the higher UGB, so your PSR tanks. It has both trade-offs. So depending upon what you want, you need to design like that. Again, I'm not going all those things here, the lack of time. So chopping itself has problems. Yeah, sorry. Okay, so you can do chopping at the output. If you do chopping at the output, as I mentioned before, your input frequency, your input is a DC here. It goes to a chopping frequency, right? Because of the input switches. Now it will see the gain at that frequency. Let's say chopping frequency is for the argument's sake 1 megahertz. Now your input will see the gain at 1 megahertz, which may be lower. You're not going to see the DC gain of the amp, right? You get what I'm saying? Let's say that you have an amp with a loop gain like this. Fine. You might have designed an amp with a DC gain of, let's say, 60 dB, argument's sake. Nice, you spend a lot of effort in designing the 60 dB gain. Now, what did you do? You took the input signal, which is DC, and translated to a higher frequency. Let's say 1 megahertz is somewhere here. Now, the operation amplifier will only see a gain of maybe like 20 or 30 dB at 1 megahertz. Let's say argument's sake 20 dB. You're not going to see a 60 dB gain for a signal. Ideally, you want to see the entire gain what you designed for the signal, but you're only going to see about 20 dB, which is a bad. If you're going to do chopping at high impedance node, output is a high impedance node in our OTA. That's why that in order not to do this, you go and do chopping on the low impedance nodes. So you will not, at the low impedance nodes you're not going to kill the gain. So that's why that's a good idea. What's that? The operation amplifier is only one stage. There's only one stage, that's it. Because you have an operation amplifier followed with that PMOS current on the bandgap core. Already it is 2 stages. Now, if you make the operation amplifier with 2 stages, then it becomes a pain for compensating. No, first stage is one what you need to chop. Second stage you don't care. So you do the first stage chopping, second stage you don't care. So typically, if you do a chopper, the most prominent architecture what I have seen in my experience is like you do the chopping 2 stages and you put a feed forward path, so that you don't kill the UGB. That will take care of the high frequency, and this will take care of the low frequency, and overall you'll be fine. So that's the architecture I have seen. If you do it at a high impedance node, you will not get. If you do it at a low impedance node, you will get. It will not get affected a lot. Yeah. So this has been explained nicely in 2001 JSACC by Kofi McKinnon. 2001 JSACC Kofi McKinnon. Yes, explained the nice thing about chopping, where to do, why not you do this and all. Okay. And this is a notch filter. So this is nothing but a sampling circuit. We know that if you take a signal, you sample the signal at the same frequency, you get a DC. Okay, there's a known thing. So you take a notch, you get a ripple, you go and sample at the same frequency, you will get a DC. So there's no ripple after this, and that's what people typically do for their notch filters. Okay, I just talked some issues with the chopping. I'm not going to explain how we handle it. There's certain issues with the chopping is like low frequency noise filtered up to F clock. So you need to have a higher, you need to have the frequency lesser than the noise, otherwise you'll see aliasing. So you need to do switch capacitor action at the low impedance node, what I explained you before. And you'll see that at the input, you'll see a parasitic capacitor. You keep swapping the input. So some parasitic resistor developed, and that spoils the accuracy of the bandgap. You have some current going to the parasitic resistor, and that eats up into the error budget. And you get an output ripple. So if you have an output ripple on the operation amplifier, if you have a second order nonlinearity, which typically you will do, it's a single-ended design, and that creates a DC component, and that DC component gets amplified with the p-type gain, and that gives you some error sources. And there's much more to that, okay, which I'm not indicating here. The only few issues what I'm indicating here. For example, if you have a resistor at the virtual node of the operation amplifier, it lowers the virtual node impedance of the operation amplifier, and hence the amplification factor of the offset and flicker noise becomes higher. We should not lower the virtual node impedance of an operation amplifier. If you do chopping, you will indirectly. How much it depends, but you will do something to that. But this is only note. What is not yes. Jitter. If you take the average to be 0, then it should not. If you take the average jitter to be 0, then it should not. But if you have a skew, let's say that the chopping relies on 50% cycle, right? Now instead of 50, you have 49 and 51. then you'll have a residual ripple. You'll have something to that. Okay, then I'll talk about the current mismatches in diodes. It's simple to analyze. Now let's say that you have a delta I mismatch between the two current sources, and assume that your impedance of the BJT is 1 by GM. Now the delta I will flow into 1 by GM, result in the delta VBE. So this error of delta I by GM at the bandgap output is typically small. I don't pay much attention to that. If you really worry about it, you go and size the transistors. Don't increase the width, increase width and the length by the same amount, or they degenerate. The best thing to do is a degeneration instead of increasing the size of the current sources. Or if you really want, you can chop it or rotate it or do whatever you want to remove that other source. Okay. Beta mismatches. So ideally, we should neutralize the collector current. Here we are neutralizing the emitter currents. And if you replace in the equation emitter and the collector current, you will see that you will see a beta 1 by 1 plus beta 1 into beta 2 by 1 plus beta 2. Sorry, it's actually beta 1 by 1 plus beta 1 into 1 plus beta 2 by beta. It's a typo. Okay, it's 1 plus beta 2 by beta 2. It's not multiplication of beta 1 beta 2. It's a small mistake here, but the takeaway is like beta comes within the log term, so typically the error is small in this architecture compared to block out. Block out comes directly, here it comes within the log. So that's the trade-off. So here your operation amplifier offset amplifies, there's no operation amplifier, but beta shows up there, here it doesn't show up. Okay, again we'll go with some more architectures. Fine, you get a p-type current, you take one more diode, put into p-type current, put a resistor to convert to a V out. Advantage is again two operating point. The disadvantage is that output cannot be less than 1.2, requires more BJTs, requires higher power supply. Now, one more thing, what you can do is that like, hey, look, the power supply scales with technology, or as we know, we have 1.2 volt, we have 1 volt, how are you going to design reference voltages? Solution is that like you add CTAT and PTAT information in the current domain, not in voltage domain, and then convert that constant current to voltage back into the resistor. That is precisely done in bandbar. This is a bandbar network where RP converts PTAT current, RC has a CTAT current. You combine this into IGTAT, put it into RF to get a constant voltage. Interestingly, this has several problems, like you can see multiple operating points. There's not only two, there are multiple million. In the low, especially if you look at the low bias currents, there are million operating points. The reason is like you're shunting a diode with a resistor. RC is shunting the diode. So at very low bias currents, what happens is all the current goes into RC and the operation amplifier stabilizes. Okay, this is a big problem. Designing the startup in bandbar is challenging. Another big problem what we have is you don't have a PTAT. PTAT current is gone. You only have a CTAT constant current information in this architecture. So for circuits which needs PTAT, you need to have one more circuit to generate PTAT. Okay, it doesn't give automatically. It's a nice thing. We lose in bandbar. Okay, so in order to do this, what we do is there's one more architectures in the sub 1 volt. Hey, look, I will not put a resistor. Rather, I'll put an operation amplifier to convert a CTAT current, and then I will add the CTAT current with the PTAT current, like you do here. Typically done in industries this way. So it has only two stable operating points. Startup is easy, and PTAT current information is also available. Well, talking of startup, I just want to mention here that like at the time of startup, the operation amplifier itself puts a bandgap and a positive feedback. You can think about it. I'm not going to explain, but it's a very interesting question. When the current is zero, if you look at the polarity of the operation amplifier, what you have here, it becomes a positive feedback. That makes the circuit not to come out at all. That's again a pain. So this we developed in our lab. So there's a voltage mode, there's a current mode, and we call this to mixed mode reference, because what we did was that hey, look, in sub 1 volt we cannot design a bandgap because CTAT voltage is 800 milli, more than 800 milli at minus 40. So what we can do is why not we divide the CTAT voltage and then add a PTAT. That is precisely we did. We took a CTAT voltage. Operation amplifier 2 will give the CTAT voltage at X node. R2 and R3 will divide the CTAT voltage, and you add the PTAT voltage through a R4 current. You take the PTAT current, amplify it to R4 and add at the center node. That gives advantages like it reduces the number of error sources, and the design of startup is very straightforward, and PTAT current information is still available. And this became one of the most popular articles in June 2021, TCAS2. The design for 24 TSMC 45 nanometer is based on only simulation. And yeah, We published in April. It became a popular article in June 2021. So with this, I will hand over to Rajshekhar for take over for moving the slides. And thank you all for giving me an opportunity to present this work here. And thank you once again. So Rajshekhar.
Thanks, Rakesh. It was nice.
Thank you.
Thanks.
Thank you. Yeah.
Rajshekhar, can you hear us?
Hi, I can hear you. Or if you can stop sharing from your side, then only I can share. Actually, it's not allowing me.
Sure. Yeah, sure. Please go ahead. You can share.
So I'm sharing. I had unfortunately had an issue with the multiple screens. I don't know how to.
Right now, you can see it, sample bandgap architecture.
Yeah. Okay. Perfect. Then 1 second. Let me.
Just probably full screen.
So let me. So can you see?
Yes, systematic offset. You are changing slides.
So good morning, everyone. Thank you for attending. So unfortunately, I was not there. So I'll try my best to answer questions from the audience. Otherwise, Rakesh or Sauri can take the questions. So feel free to stop me any point, and then I will try to share a paint and try to draw in case if it is requiring. So
we'll take for 15 minutes and then take a break, Rajshekhar. Is that fine?
Okay. Yeah, that's fine. That's fine. Just tell me when I had to stop, so I'll stop immediately.
Thanks.
So far, what Rakesh has discussed is the principle of the band gap, and then what are the traditional and very popular architectures which are available, and they are mostly used in our wireless and wireline systems. And slightly, there are like few outcomes of those 3 architectures, and the present architecture what I'm showing is a sample band gap. Can everyone see my cursor movement here? Okay, so the main disadvantage of the all previous 3 explained architectures are not only those 3. On most of the architectures is the offset of the op amp is multiplied by the PTAT gain, which is 1 plus R2 by R1, which is like traditionally 8 point something for n equal to 8. And the offset of the op amp will be amplified. Why? Because the op amp cannot distinguish the difference between the PTAT, because originally the op amp is to amplify the PTAT so that it will cancel the CTAT and PTAT gain, PTAT temperature coefficient. But unfortunately, the op amp cannot distinguish between the PTAT or offset. So it will amplify the offset also. And so the final output is like kind of like VBE plus alpha times alpha times PTAT plus alpha times offset also. We can trim this offset, so the mean is not a problem, but the temperature drift of the op amp is temperature drift of the offset is problem. So that's why this architecture has been developed as Rakesh and his group. So basically what he's trying is, so till now the approach is take the VBE and that is a CTAT, and take the develop the PTAT and amplify it. So that's why this offset problem is coming. So now why can't we go other way around? So why can't we take the VBE and scale it to the same ratio and add it to the PTAT? So that approach also will give you the same, but it will give you slightly lower voltage, but the offset doesn't even come into the picture here. So now here, so the introduction is so basically we generate a VBE1 and VBE2, and through a switch cap sensor, switch cap network is it's like a kind of low pass network, and generate VBE2 minus VBE1 and generate VBE2 and scale it down. So you can see here, so what is happening is, so VBE1 and VBE2, first of all, what you're doing is, in one phase, we are charging capacitor C2 to VBE1 and C1 to VBE2 minus VBE1, and that is the first phase, so that all the capacitors are charged with these voltages. And in the next phase, when we turn off this charging phase and when you turn on the, we ground this capacitor, left node to the ground and connect this to the CL. So what will happen is, so the final charge, if we apply charge conservation here, the total charge on this capacitor, output capacitor, is VBE1 minus C1 by C1 plus C2 into VBE2 times times 1. Forgot to explain. So basically, if you wanted to generalize any band gap voltage, so the broker will come like this: VB1 plus VB1 minus VB2 times alpha, where VB1 is the BJT with higher current density. So this term, this VB1 plus VB1 minus VB2 times alpha, is the broke over any what you call high voltage band gap. Now when it comes to Bamba, so this entire expression will be multiplied with scaling factor. Typically it is half kind of thing, but it can be lower than that. So now in this architecture, so basically instead of doing this alpha multiplication here, what we do is we adjust the VB2 such that it will cancel the temperature coefficient. And so this is the typical case in the Bamba and all, where alpha equal to close to 9. Again, it varies all over, like 7 to like even sometimes it cross 9, depends on what kind of VB1. But these days the BJTs are so tiny compared to the older technologies, so the current density is really high. So the temperature coefficient VBs keep coming down. Like if you see 90 nanometer, and even before that, it used to be like 1.8 millivolts per degree, but these days I think 1.5 millivolt per degree. It's quite common. Even 1.4 also I have seen recently. So the alpha is like function of, only thing is that we can only check this through lot of simulations. And so anyhow, finally the voltage of the capacitor is exactly what you want, but in other way around. And this, the timing diagram shows which capacitor is turned on which side, and the output tool is available in the 5 bar. So the available voltage here is, if you see, it is slightly it's lesser than the traditional circuit, because in traditional circuit we take the VB and multiply the PTAT, but here you take the PTAT and then use the scaled version of VB2. So these are the expressions. I'm skipping few slides because I have a lot to cover, but I mean I'll try to cover the mostly fundamentals, and then which are like design techniques, than existing literature and measurement results. And this is the final implementation. So you can see here, let's focus only on this side. So let me find this. Yeah. So now, so you can see here, so starting from this point, so far we are here. So I mean, this is the time interleaving we have used, but for now just focus on time interleaving. Means we just swapped everything so that vertical output impedance will be decreased. But you can see, so the first we have one VBE, which is sampled on the capacitor. In that phase, VBT is sampled on the output capacitor, and in the another phase, just time interleaving, we just swapped. So for now you can consider that only one capacitor is charged and reverse it. So in this case, what I'm, the VBG is according to this expression, and the alpha is adjusted by C2 by C1 plus P2. Here actually C2 by this C2 by C1 plus C2 makes it's a very important factor, because that comes under loop gain, because the VBE2 is attenuated by the divided by the C1 plus C2 by C1 by C1 plus C2. So that comes in the loop gain or noise expressions. And here if you see, so how to bias these legs here, right? So what we have done is take the band gap voltage, like assuming the band gap is stable, then generate a current which is VB by R2, so VBG by R2, and mirror it back. So that is how it works. And so to match the temperature coefficient VB2 and PTAT, so use this kind of capacitors. Like it's exactly same as how we do in band gap, voltage mode band gap, where we adjust the resistor ratios and we trim some resistor ratios. Like that here, a capacitor being designed. So now since the voltage is like the voltage looking at this point is low, like 100 to 200 millivolts typically, so we used a PMOS what do you call PMOS OTA or op amp with a cell bias. And as Rakesh explained, the cell bias is to minimize the minimize the systematic offset by mostly equalizing these two nodes. Like traditionally, okay, first of all, right, this is the PMOS OTA, and this is the lag compensation, which I have a couple of slides to, like, there are a lot of pitfalls and misunderstanding on this RC, how it works. I'll take this at the end of the tutorial. So basically we take this current and put it, dump it in the back, so that all VGS and VDS will track. And this is the startup circuit. So in case if it doesn't start, so this will try to pull down this node, so that this node will be down. So significant amount of current will be injected. Once it reaches to state, this will be switch off, because it requires 2 VTs. So which it, in normal operation, it can't be, because this will be 1 VT, this will be another VT. And so, if the supply is greater than 4 VTs, then only this won't turn off. But in our case, the supply is far lesser than 4 VTs, so this will be shut off. And so if you see here, basically the systematic offset will be reduced through this shallow bias, because imagine if there is no shallow bias like this, there are people who does, like, shallow bias at a, it requires slightly, it's a startup required, and some people fear of, it might not start. So what they do is they don't use this kind of traditional stuff. What they do is they simply put a diode and resistor, so that it relies on supply. And as long as there is a supply, there is enough current, which varies across PVT and all, and it doesn't track offset and all, but it's a robust, so people does that. But in that case, what will happen is this node, this node and this node differ by few millivolts. Ideally, they have to be exactly same. That turn as a systematic offset. Now with this one, with this shallow bias, those two will be almost same. Like we have seen like couple of like few tens of microvolts, whereas with fixed bias, it will be like maybe it could even go a millivolt. And the issue is we are not caring about 1 millivolt or 10 microvolts, but the problem is that the temperature drift, which we can show you clearly how it shows on the DC characteristics. So now coming to the polarity. So as explained in the introduction, every band gap is like mix and match of positive and negative feedback, and then at startup the positive feedback dominates more, and that makes compensation of band gap little cumbersome and challenging, especially if you have a chopping that makes even more worse. So fortunately in this architecture, the positive feedback is like inherently it's a pretty weak positive feedback, because you can see here. So now this red mark loop is the positive feedback. If you see here, if you cut from the loop here, so we travel around this. So what will happen is go from here to here. So first of all, so the BJT, so for example, if you dump delta current into this, so the amount of, the voltage across BJT is 1 by GM times delta, and that will be, that is the op amp input. So the current flowing here is, so the delta by GM by 1 by R2, sorry, my apologies, there is a typo here, this is R2. We corrected in few slides, but I forgot here. So VB delta by GM, and that times 1 over R2. Now what will happen is this current will be mirrored, and so what happens here is when current dumps here, the difference current will see as I said in the previous case, it will be scaled by C2 by C1 plus C2, because that's where the total voltage is sampled and VB1 and VB2 subtracted due to the division. So the loop gain is multiplied by C2 by C1 plus C2. Whereas the negative feedback, if you see, the negative feedback is different, because basically what will happen is it's in the negative feedback, you have total gain of much higher, because this loop, right, this loop much more dominating actual, right? So this is the negative feedback. So if you see the positive feedback loop gain is far lesser than 1, the negative feedback is much higher actually. And this is even similar in the startup, so which is very advantage compared to the existing architectures. And so one more thing is the PSRR of this architecture is quite good, because it's so basically the band gap is relying on the low impedance nodes, and then the output is generated the low impedance node. Whereas if you see traditional band gaps, whereas like, I mean, it's generated eventually, whatever be the architecture, eventually it will be a PMOS and a resistor. It will be generated here actually, which is, this is generally like 10, 15K. So the PSRR is like, it's not, I mean, at low frequency, it's good, but once you come to the couple of like megahertz, and there won't be any loop action on the PMOS gate because op amp is dead. And so mostly the power supply is leaked through, and the effect is more here because of the high impedance. Now here, luckily the diodes are there, so which are I mean, very low impedance. So the PSR is far better than existing one. And these are some noise expressions, mostly, I mean, these are derived. And the take is, one important thing is the OTA has no influence here. As I said, there is no amplification. And one more thing is, these current sources, these two current sources are current source noise is going to the low impedance nodes, and it's not amplifying. So the effect of these also, I mean, the effect of current sources and op amp is quite low. And so most of the noise at the output is generated with this transistor, because that will be fallback. But like, it's a, so basically op amp is not the main one in this one compared to the traditional band gap, Bamba or anyone. So now also in the if you wanted to quantify how much offset of the op amp will be appear at the
Hello.
output. So
Sorry, I have a question.
yes.
It is about the noise impact from the ground side. Because in the switched capacitor circuit, I can see many capacitors connected to the ground. And if there is a noise coming from the ground side, how it can impact the performance?
Because see, yeah, that's a good question. But that's there, not only, that's not a relevant, that's not only the scenario in this band gap, that's common for everything. But my point is, like, we have been like, so far, like, we have few slides later. So far, my concern is how the offset of the op amp will be amplified. That has been solved. Now coming to your question, so let's say this is our band gap. So mostly we put like the decap solves us many problems. So now, so provided you have enough decap, so these two are synchronous. So now if you have, if you switch cap has any noise on this ground, that will go here, right? So these two nodes are almost like synchronous, right? So like checking the PSRR, like if we find the PSRR from this node is low, that means according to me, we haven't checked that through substrate here. I mean, so these two nodes behave in the same way. So the PSRR VDD and PSRR VS are same. And so that according to me has almost no effect on the PSRR. Like whatever PSRR from VDD, sorry, how the PSRR transfers from VDD to output, that should be exactly, the VSS also should transfer exactly like same way, which is again in the is common in like exactly same, that the way the noise transfers either from power supply or VSS to the output is same, but the magnitude is suppressed because of the low impedance nodes at the BGT.
Thank you.
Thank you very much.
Rashikar, sorry, can I
yes,
pause
yeah,
for some time, Rashikar?
yes, yeah,
If you are in between, I'm fine.
that's fine. I think I'm done with this slide. So I think let everyone take a break, and then we can freshly start from here.
Okay, sure. Then we'll take 15 minutes bio break.
Yeah, thank you.
Okay, thanks all. We'll resume back at 11:15.
So I'll be
yeah, you can
like,
stay online, Rashikar.
yes, yeah.
Thanks. So please do request us. Volunteers are here if you need anything. We'll resume back in 15 minutes.
Well, is everyone back?
Not at Rajshekhar. I'll tell you.
Okay. Maybe like we can use this time for a Q&A session if anybody interested.
Sure.
Yeah.
Are you able to
Yeah.
see us also? We have enabled camera. You can see me, right?
Oh, yeah, correct.
Okay,
Actually,
sure.
okay. I didn't notice it. Yeah, I can see.
Okay, sure.
Yes, I can see now. Okay.
Sure.
Almost like 4 or 5.
I think close to 5 minutes. We'll be back.
Yeah.
Fine.
Okay. Yeah. I mean, in the audience, if anybody want to discuss something, I think this is the right time.
Sure. We'll start back in 5 minutes or so. If you are all done, please do stabilize. We'll start in 2 minutes.
All please settle down. It will start in 2 minutes.
Rajshekhar, I think you can go ahead.
Okay, thank you. So welcome back again. So far, what we have seen is the first order first order compensated band gaps. That means, we are assuming that like the excuse me, we are assuming the VBE scales. The VBE varies with the temperature in a linear fashion, which is like, as Rakesh explained in the very initial slides, that is not true. And like, again, just to give a recap, so this is how we assume, like they assume that the VB is changing, and then this is PTET. PTET is pretty linear. That's, I think, one of the most linear and predictable parameter I have seen in my life, actually. Like the hand calculated one and then the simulated one matches very closely, like relatively very close compared to the other parameters, whereas this is the VBE will have like this. So now we are assuming that assuming that this is like linear and compensating. So that means we are leaving this curvature bits, and that will give the curvature error, actually. That means like if you compensate for first order, you get like this. So these two are the responsible for the curvatures. So now Professor CVDs and some other people in 1980s has did a lot of R&D on how this curvature and how to model this. So that looks like this. So this is very easy. So VG of T is that, that 1.2, which is for silicon at low temperature at 0 Kelvin, not sorry, low temperature, 0 Kelvin. And this is for the first order linear term. And there is a another term called eta minus alpha times Vt times ln of T by Tr, whereas Tr is the reference temperature. So now, what is this alpha? And sorry, what is this gamma and eta and alpha? So the eta is how the mobility varies with temperature, like some technological parameters. I'm also not an expert. I just use this expression just to come up with the strategy to do the compensation. So the alpha is an interesting parameter, which is the temperature exponent of the BJT current. Like, for example, if BJT current is T power 1, T power alpha, this will be alpha. So now, for example, if eta and alpha are exactly same for somehow, which is impossible according to me, then there won't be any curvature term at all. So now, how to compensate for this? This term? So, I mean, the idea here is, let's explore this parameter alpha and see, can we do something to extract this nonlinear term? So what if you use a constant current in the BJT? So that means alpha equal to 0, right? Because T power 0. So it will be like this. What if alpha equal to 1? It will be like this. Now, what if we subtract these two? What will happen is these terms will be cancelled and only the VT ln ln term will be extracted, right? So now that parameter can be that parameter can be used to generate the nonlinear term. Okay, I hope everybody understood the principle. We'll go to the implementation. One important thing to be noticed here is if alpha is higher, the curvature is lower, because eta is roughly 4 actually. So that means if roughly, I mean, I'm not exactly sure how it varies, but like it's certainly roughly 4 can be assumed. And so if you see any band gap which had been discussed so far, where the current through BJT is a PTET, which is magic, because of that, the alpha equal to 1. So curvature is a little bit more compensated by default with a PTET current. If somebody tried a band gap with BJT current, constant current, that would have been a lot worse. So let me go to the next slide. So this is how actually I described earlier. So this is the normal first order compensation. This with the nonlinear term. So you kind of like see a, I mean, it won't be a kind of umbrella concave curve. It will be like kind of sine wave. And this is the first implementation by Professor Malcovati from Italy, Pavia University, Professor Malabarti, sorry. So what he had done is, so this is the traditional current mode bandgap, right? Current mode bandgap. Now, so already these BJTs are getting the PTED current. So that means this expression is solid. So this is ready. Now how to generate this? Because it needs constant current. One advantage of, okay, maybe disadvantage if somebody want PTED, but what advantage of the Bamba bandgap is the constant current is available in this leg. So why can't we use that leg to bias another tiny transistor? Now, this voltage is, second equation 2 in the previous slide. This node is the equation 1 in the previous slide. So why can't we use a resistor so that this will draw the current? So since the op amp is a balanced circuit, what we need to do is we have to use two resistors so that the current through M2, the current through M1 is having, apart from PTAT plus so this is the PTAT current, and this is PTAT current, CTAT current, and non-linear. So total 3 will flow, and that will be like this. So this VNL is something what we extracted here, right? And so this is how actually they got into like close to 10 ppm per degree in like 10-15 years back. So this is very, according to me, the very first what do you call CMOS implementation of the curvature compensated bandgap. So if so yeah, I'm not going to discuss that. We are running out of time. Not going to discuss the measurement results and so many other details. But I hope everybody understood got the point of how we are going to compensate it. So one more very important and a lot of people ignoring is these resistors will create a lot of problem actually. So these 4 resistors, because the op we should keep the op amp both nodes as high impedance as possible. Any low impedance on those nodes will amplify the offset. As explained in previous slides, it's in traditional bandgap, it is 1 plus R2 by R1. So these all 4 resistors will decrease the op amp impedance. Then if you do some math, so decrease in impedance will directly increase the op amp, the final offset voltage. So the idea is like, the future developments and all, if we can eliminate any resistor loading, of course they are enabling the curvature compensation, but if we can find some other way, there are people what they tried is, instead of using these 2 resistors, which I haven't included here, take this voltage, use a V to a converter, and specially generate another current which is not INL, and take this current and sum it at the output, which is also works. But that had it requires so many multiple op amps, and multiple op amps create multiple offsets. So that had a problem in a different direction. So this is one very popular architecture. So this is a few more details with as a reference. So if somebody is interested, they feel free to read this. And this was done in the BiCMOS technology. So that's why also they implemented op amp with pure BJTs. So that's why they got very low offset as well. So now there is one more curvature compensated bandgap which we developed 2 years back, and which was published in ISCAS. Again, I'm going to discuss the principle only. We are running out of time. The idea is, why can't we take the existing existing Broco architecture and see, can we do something can we inject any non-linear terms? It doesn't need to be T learn T. Like for example, we can include a T square term, some weak T square. We cannot include the very strong T square because that will create a much more problem than compensating. So the idea is, the beta of the BJT has a positive temperature coefficient. So now a simple idea is, why can't you put a small resistor in the base so that the voltage across RB is beta times RB, whereas beta is proportional to T as well as T square, which a reference had been included. So this will add another nonlinear term. And so now when you had a nonlinear term, how to include this to the actual bandgap? So that is, so this voltage is equal to VBE1, right? VBE1 equal to VBE2 plus RE plus IRB. So that means the nonlinear term had been virtually added into the expression. So now how to generate the final bandgap? So what we did is, we took the BJT VB and scale it down. So this is our CTAT voltage. Now take the PTAT current and flow dump into another resistor. So this the voltage across R1 is the PTAT resistor, PTAT voltage. So the total voltage is voltage across R1, which is the current times the impedance here is R1 plus this is not a ground, right? So R2 parallel to R3 plus the scaled version of VBE. So I'm going to skip these things, and you can see how this is what I explained, VBA1 equal to VBA2 plus IR plus RB. So that this is the PTAT current. And so you can see how the PTAT current has been included the beta. So now this is the crux of the proposal. So now you can see the beta is like beta naught is a strong one, and this is a little weak, and this is even weaker. So this has been I think it did like in this paper, the beta variation with respect to temperature had been given very clearly how it is going across PVT and all. So if we plug this into our equation back, you will see some kind of compensation. Though it is not V till on LNT, we are including the T square, which is like some kind of like a semi curvature compensation. And like there are so much of math, and then anybody can refer one of our references. And it's like it's mostly how the errors of the each and every like op amp offset, and then how the current mismatch between the PMOS and all. So they can, I'm going to skip this. Like I'm trying to, like I have another like 15 minutes maybe. So this is one thing which I wanted to cover. So how the startup had been verified, which Rakesh explained briefly in the previous introduction. So again, we add a op amp battery here, and at the op amp output, and then sweep this voltage. So what you can see is, so this is the that curve. The interesting thing is it should cross the zero crossing point only at one point. So that says only one operating point. But another interesting thing is this point. So when the PTAT voltage is very high, right? Sorry, when this output is very high, the op amp will steer to one side. So what will happen is, this says that this is the bias current of the op amp. You can say that. So this is the bias current of the op amp, and this has been run for 3 different temperatures. So you can see this could be at very low temperature corners and mid typical, and then like maybe this high voltage. That's why. So these are the bias currents, and this is like depends on the total op amp design. So that is something interesting recipe you can take, and by looking at this you can see is it biased properly or not. So these are the supply sensitivity, PSRR and all, and this is a noise. Like noise is not great, like 276 nanovolt per root H, and this is like how it had been laid out, and mostly dominated by, like most of the band gaps area is dominated by either BJTs and resistors. So now another interesting thing is these days the supplies by the way, any questions so far before I jump into this slightly? That is a curvature. This is the how to design a traditional band gap into very low voltage technologies. So if any question, please stop me. Otherwise I'll move on to this. So now how to
1 second, Rajshekar.
Yes,
Somebody has doubt.
Yeah.
Can you go to a couple of slides back where VTest is applied?
Okay, this one.
Yes.
Yeah.
So that VTest you mentioned at M1, M2, M3, VT is connected to PTEL node, but you applied at VC where BJTs are there. How to test that one? Test is working.
Oh, I mean, okay. So, yeah, sorry. Yeah, it's not here actually. Okay, for this one, yeah, I mean, what I mean to say is pick any low impedance node, right? Any low impedance node, and try to adjust like basically, okay, the idea is, for example, I mean, let's try to talk in a very generic way. So take an op amp like this, okay? So let's apply 1 volt here, you get 1 volt here. Now, if you want to see the what do you call how many operating points, okay? Though, I mean, consider that this is like a very standard op amp. Now put a voltage source here, okay? What will happen? Let's say if I apply exactly 1 volt here, nothing will happen, right? Because this node will, like this a KVL, right? So this node is at 1 volt and we connected on volt, so no current will flow, right?
Yeah.
Now let's say, so this is 1 volt is 1 operating point. But like why this test is important is there could be some hidden point of, let's say, like 0.3 volts, though our DC sweep is different, DC operating point is different. Like sometimes cadence rate magic, I mean, any circuit simulator magically catches this 1 volt. Okay, there could be several operating points. It could catch this 1 volt and live there. But we need to see, we need to what do you call experiment all voltages and see whether it will travel through the 0 to VDD and see is there any stop points rather directly landing to the actual point. So now what will happen is, if there is a operating point at 0.3 where the op amp is happy, right? So that means the moment we put a 0.3 here, if this is also 0.3, then again it will be happy, right? So happy in the sense, like if the both are fighting, then it will be, a lot of current will be flowing into the, like, because see, this is a strong voltage source, right? If you apply one, or let's say 0.8 volts, and this is because this is a weaker 1 volt because there's output impedance, and this is 0.8 volts, very stronger, so this will try to dominate this, right? What it does is they both keep fighting. So check the current crossovers where there are like multiple zeros. I mean, this is the reason, if you see, we tend to power down all the every node, so that when you start, it starts from the known voltage, right? That's why we put every node to ground or reader wherever a known potential, rather leaving things on the floating, so that they start from a known point which we all simulated properly. Whereas if you leave floating, so that could start from any voltage which we don't know whether it is a stable point or not. Does that answer your question?
Yes. Yeah.
Thank you. So I need to be a little quicker. I think less time for me. So now, how to design a low voltage band gap? So what we can do? Can we decrease the band gap voltage straight away? No, because the one of the major contributors, the VBE. So you can see the VBE varies with the temperature, as I know, and this is the current and this is the voltage. With respect to temperature, if you see, at very high currents, low temperature, you are almost like close to like 890 millivolts or something. So that means that limits the, like, by looking at this one, we know that at any point, like, we cannot bias this is like less than 950, because we need to leave another 50-60 millivolts in the worst case to the PMOS current sources. So now how to minimize this? So one simple idea is, why can't we travel in this direction and say, okay, I'll be here. So my maximum voltage is 0.7. So that decreases 200 millivolts minimum requirement of the supply. Can we play this game for? Yeah, I mean, it looks beautiful here, right, from this curve. But the downside is, if you see the sigma of the VBE, because ultimately the accuracy depends on sigma of the VBE. So at lower current, the sigma is very high. So that means, I mean, at, let's say, by this one, you cannot cross like, maybe like, half a 0.1 micro or something is the right point actually. So can we do this? So that means from BJT point of view, lower current works, but is there any other element is limiting? So what will happen is, so if you use the standard traditional band gap, where the PMOS currents in the top is equivalent to is same as the BJT current. So what will happen is, in this one, so very low current for the transistors, the MOS transistors, there will be a lot of mismatch. There is a lot of mismatch. So basically, to improve the mismatch, we need high current in the MOS current source and low current in the BJT. So how to like, in the architecture, what we have is they are exactly same. So what to do? So that the idea we came up with is, like, this had been, we published like 2 years back, I guess, which we had indexed in the reference, so anybody can read this full details. So the idea is, so this is the PTED current, bias the MOS with high current and bias the BJTs with low current. Okay, so what will happen is, take this BJT current and so let's say this is I, and subtract some current from here, so the BJTs will draw less current. So that means they are happy with high current. These two are happy with low voltage and without having any mismatch problem. And so the rest, I think the rest all you can see the supply sensitivity you can see here, it perfectly works up to, like 820. And again, this is limited by the, low -40 degrees temperature corner. And so, yeah, again, one more recipe everybody can use is the supply sensitivity, how this is related to PSRR. So check the slope, like, like take a safe flat area and check the dV by, D output by D supply, and that should be very similar to your here. I think what you noticed is it's almost like 1 by 85 or something. So that is like close to -40 dB. It's much slightly higher than -40 dB. So that, by looking at the PSRR, you roughly know this, how to guess PSRR, low frequency. This is the shallow bias op amp, which we had discussed earlier. And yeah, this is something which I wanted to focus. Maybe I have seen, so many people have doubts about this compensation. So usually how we do a band gap compensation is we don't use the traditional Miller, though it is a popular workhorse of most of the ADCs and all. And if there is any PSRR requirement, we cannot use a Miller here. What will happen is if you use a not mirror, sorry, apologies. So any supply noise you put in here, that will come through the VGS of the M1 and it will enter into the output. So the Miller provides a high frequency path into the output. So generally most of the people don't use Miller. So what can we use? They use simply a lead lag compensation, RC network here, which is like, a capacitor and a resistor, and mostly this is done with a MOS. And basically what this does is, as a rule of thumb, which I found out like over the last, like, I have designed a couple of band gaps and then other circuits. So this can be very useful approximation. The CC is like, close to, there could be some exceptions, which I will explain in the next slide. The CC is almost like maybe like 10 times or like close to 10 times of what node capacitance you have here, total capacitance to the supply as well as the ground. And the RC, like most of the people might have noticed, the CC is come like couple of picofarads, because this output may be like like half of the pico or something. So maybe if you multiply 10 picofarad, the RC usually 3-digit ohms, like 500 600 ohms, because the RC has to be 10 times lesser than the total impedance here, equivalent impedance, which is like mostly op amp. So check the op amp output GDS, and that will be like maybe 10-15 times lesser RC. So now how this works actually, that is like have seen a lot of students been asking about this, so how this works. So now let's go to this. Let's try to understand this network. Let's say you have and for time being, assume there is no this RC and CC. You have only R1 and C1. R1 and C1. This is the dominant pole. So what will happen? You have a pole here. Now what will happen is 1 by R1 C1. So let's say this is the dominant pole, 1 by R1 C1, and there is some non-dominant pole in the op amp or something. Okay, like somewhere in the band gap. So now how to improve the phase margin? So what we do is stick a RC network here. Basically our idea is we want to add something here which will decrease the decrease the high frequency resistance. Not, okay, my point is, so basically what it does is, so initially without RC and CC, you have, let's say this 0 dB, or like if you multiply the op amp, so this is 1 by R1 C1. So by including RC and CC, what will happen is, so your dominant pole will be like 1 by C1 into R1 plus RC. Let's say RC is very less compared to R1. So it's a 1 by R1 into CC. And as I said, CC is like far higher. What will happen? This pole originally, like it will move back actually. So that means this is before compensation. So after compensation, this node will move here. So there is a dominant pole will be moved, and that is mostly dominated by CC and the op amp output impedance. Then what will happen is there is a pole zero doublet forms.
Rashika,
And
sorry to
yeah,
interrupt.
yeah.
I mean, how long it's gonna take more?
I'm going to stop like in another less than 5 minutes so that Shauri can take over.
Okay, sure.
Yeah.
Sorry, thanks.
Yeah, I mean, we are running out of, there's a lot of material. So I'm sorry for that. We didn't plan properly. So, so there is a dominant pole which had been moved to low frequency, and there is a 0, 1 by RC, CC, and there is a high frequency pole, which is like 1 by, C1 times RC. Whereas, as I said, the RC is very small. So, C1 is the parasitic. So this will be much higher. So what is the advantage of this is the dominant pole is gone down, and there is a 0 formed. We generally what we do is we make sure this 0 is close to the second pole, dominant pole of the original network. So these two will be cancelled, or like slightly it becomes a little messy. But like the point is, it is your dominant pole will go down, and then your dominant pole will go down, and second dominant pole will increase, provided these two compensate. Like they don't need to compensate, but like they have to, if you see the phase, right, it will come with like -90, and there is some little bit of glitch and comeback, because that is a separation of the pole 0. So here it's almost like a Miller, but without having any high frequency power supply coupling. So that's the end of the, I will take another maybe less than 5 minutes, and end of the literature survey, and then design techniques. And if you want to design a band gap, I quickly go and you can refer these slides. What you have to do a band gap properly. And as I said, it's mostly characterizing the BJT. You need to select the how much current you need. So basically, very low current is good from the parasitic resistance point of view, but at the same time, if you see the beta versus current, at very low current, the beta is dropping. So that's why you cannot take very low current. And how to take the BJT size, and just sweep the current and see, and what is the minimum voltage you need. So that is how you take the BJT. And how to choose N, this is a long story. If we take very high N, what will happen is the amount of offset amplified, the amount of op-amp offset amplified, the output will be decreased. So higher N is always good. In fact, I have seen like people like Qualcomm, they used N equal to 300 actually for low noise band gaps. I mean, low noise VCOs and all. But the another problem with using high N is, if you use high N, then you need to use more current, because the current of the band gap core has to be much higher than N times IS at hot corner. So IS is not in your hand. If you take more N, you need to increase the bias current. So this is how the mismatch has been calculated. And the important thing is the current, the PMOS current mirrors mismatch only depends on the W, not on the L. And this is how, when you design op-amp, what you need to look for is, so when you have an op-amp like this, right, the important point to be considered is the input voltage of the input common mode of the band gap op-amp is having the CTAT nature. So what will happen is, at very, like at low temperature it's high, it's keep coming down, the diff pair output, whereas it is kind of PTAT. So we need to look for, I mean, it's like this is like, you can see the diff pair can go into triode. That's why most of the time the PSRR at low temperature is very poor compared to the high other temperatures. So that is mostly because of this problem. And this is how the the output versus temperature, and these are first order compensation, and these are the across PVT. You can see it's almost like 20 ppm per degree for this low voltage band gap. And temperature, yeah, I think that's sorry, I had to go very quickly. So if you have any questions, maybe 2 minutes we can try, and then I'll hand over to the Shauri. Or if there are no questions, that's the end. Thank you very much.
Thanks, Rashika. It was nice presentation.
Thank you very much for your attendance.
Any questions?
Thank you. I'll stop sharing then.
Yeah, one question looks like.
Okay. Yeah.
You mentioned in the compensation, the pole 0, right?
Yes.
How that settling of the op-amp output, it will take so much time, or
Sorry again, can you repeat? Can you be a little louder?
The transient behavior is not same, because we are canceling pole 0 at the
Yeah, Agreed. Yeah, that's the problem with any pole zero compensated. But like, yeah, to be frank, what you said is correct. But we are not, things like bandgap and all, where we are not looking for 99% settling and all. See, that pole zero doublet only will happens, I mean, it's mostly affecting the very last bit of this one, but that settles with like, okay, take a, mostly take a capacitance of roughly, like maybe 10 pico, and then like, yeah, okay, the zero is like some kind of like, maybe close to a megahertz. So that means your bandwidth is far higher than that. So that means you have settling off in a couple of microseconds, right? Usually the problem with the pole zero doublet is the settling time predicted by your bandwidth is no longer valid because of the because of the pole inside, right? So maybe the settling time may be less than a milli. Definitely, it can't be more than a millisecond, right?
Yeah.
So I think mostly, again, I'm not very sure. According to my experiences, we let the band gap, settle. Like we give few microseconds, at least few milliseconds time, and then let it settle, and then we enable the regulators, and that is a sequence, right? So according to me, the pole zero doublet is not a big problem for this kind of applications.
Okay.
Unless you try to shoot for a very high high settling systems actually.
Mm.
Does that
Yeah.
answer the question? Okay, thank you. I'll be in mute mode. Thank you.
Thanks, Rajshekhar. So Professor Shauri Chatterjee will continue. This is not on. Is it on? Is the mic on? Can you guys hear in that mic? No,
Yeah, is it? Yeah. So we are going to diverge a little bit. So far you have seen the traditional band gaps, and we are also short on time, but I'll give you a flavor of other kinds of modern references, voltage references. And to start with, so this is a brief agenda. This is your traditional band gap, which you have seen many times by now, right? And one of the problems that you would have noticed by now is that operating at very low voltages is not possible, right? There is a limit to how low power supply you can have. There is also one more problem, that you can't afford to not burn power. So for example, this requires quite a bit of power consumption, right? If I want to target, let's say, a nanoampere, you can't do it. So these are some of the standard problems with band gaps. This is the reference. Actually, this particular one we have been talking about quite a few times. So this, you can refer to Banba's paper over here at the bottom. All right. Recently, 2012, this particular paper won the HICC Best Paper Award. It had only 2 transistors. Actually, there is more. What you have to focus on is 2 transistors. This is a paper by Mingu Seok and the rest of the Michigan team, University of Michigan team, Dennis Sylvester and David Blau and so on. Mingu Seok's paper has 2 transistors. What I have drawn is not exactly his version. It's a flipped version of his, but it's the same thing, right? I have interchanged NMOS and PMOS, but ignore all of that, right? This is the gist of Mingus-Yock's paper. His entire paper, his entire premise relies on leakage current. You would think that leakage current is something not predictable. It varies from chip to chip, but no, these days foundries have characterized leakage current quite well. What is leakage current? Leakage current is, if you think of a gate, if you think of an inverter, CMOS inverter, you've got NMOS, PMOS, rather PMOS, NMOS, right? When the switch is off, you will still have current flowing from VDD to ground. Okay, so ideally, a CMOS inverter draws current only during the switching transitions. This is ideally. But because of weak inversion, the CMOS inverter is going to draw current even when there is no transition. So suppose your input is VDD, gate is at VDD, output is at ground. All right, drain is at ground, gate is at VDD, and source of the PMOS is at VDD. Gate is at VDD, source is at VDD, right? You would think that no current is going to flow through this device. But you have VDS. VDS is one full VDD over here, right? VDS, gate is at VDD, drain is at 0 volts. Because of VDS, you will still have some current trickling through this inverter, this PMOS device. Okay, so this is the premise, right? And modern digital circuits, people have worked very hard on leakage current, and foundries have actually modeled this leakage current quite well nowadays, right? Modern processes, leakage current is modeled. Sorry. So leakage current is because of weak inversion in the MOSFET. How weak inversion? Anything, right? This is the equation for the MOSFET. This laser. Okay, so I have a mouse. All right, I really can't. No, it's fine. So you have a current, VDD is the source, VDD is the gate. So you would think that no current flows through this PMOS, but because of weak inversion, you're going to have some current, which is basically this particular expression. And if you notice, this kind of looks like the BJT equation. All right, it kind of looks like the BJT equation. The weak inversion characteristics of the MOSFET looks like the BJT equation. All right, minus VT1 is because VGS is equal to 0 in this case. So it's 0 minus VT1. The second MOSFET, presumably this current is so low that the second MOSFET cannot possibly be in saturation, strong inversion. So the second MOSFET is also going to be in weak inversion. And this also has some characteristics that is based on the weak inversion equation. Now there are only 2 devices over here. ID1 has to be equal to ID2. Now what Mingus-Yock and the co-authors figured out is that you can build a voltage reference out of this, provided these 2 devices are of different flavors. This is the catch point. They have to be different flavors. Okay, they can't be PMOS, they can't be NMOS, right? Normal analog engineers think that, if things are identical, they'll work better. But in this particular case, the two different MOSFETs have to be totally different, right? For example, 1.8 volt MOS or 1.2 volt MOS and IO MOS, something thick oxide, thin oxide, they have to be totally different. Then this reference is going to work. So what's going to happen is you're going to equate ID1 with ID2, all right? And then you're going to crank the equation. You have to solve for VREF over here. Once you solve, this is pretty much what you're going to get. VREF is going to be something like this, some complicated expression like this. Now, in this complicated expression, alpha is, again, alpha is mu1, COX1. These mu1, mu2 are different because they are different flavors of MOSFETs. COXs are different. W1, L1, W2, L2, of course, these are different. And M1 and M2, these are called the subthreshold slopes. These are also different. Everything is different. However, you'll get some ratio over there. Okay, ratio not equal to 1. All right. Finally, you will arrive at a complicated expression like this. This is simply by doing ID1 is equal to ID2 and solving, right? This is what nature is going to do. It's going to try to solve for the operating point. Now, term B over here is a PTAT voltage. PT over here is KT by Q. This is simply KT by Q. This is a PTAT voltage proportional to absolute temperature. VT1, VT2, we don't know what these are, but we can choose our MOSFETs such that VT1 minus VT2 or VT2 minus VT1, right? Either of these will be CTAT. Either VT1 minus VT2 will be CTAT or VT2 minus VT1 will be CTAT, right? Whichever it is, we'll engineer our circuit such that this one is CTAT, this one is PTAT. Choose alpha such that you cancel the slopes. This is the story, right? You can also choose this as negative, so minus PTAT, and you can have this as minus CTAT. So keep provisions for all of these in your design. That is, you can design for minus CTAT and minus PTAT. That also will work. Yes.
Regular, right? Regular PMOS. So there will be PVT, say M2 is in pass corner.
M2
is in pass corner. M1 is in slow corner.
Yeah, we'll come to that.
And how about the Monte Carlo?
We'll come to that. We'll come to that. So far so good. So we are not doing any corners right now, right? We are not doing process corners. We are not doing TT, FF, SS, or skew corners and so on, right? For a given lot, for a given wafer. So this was Mingu Siok's plan. This was his plan that he is going to do it on a per wafer basis. He is going to digitally select. So it's not just 2 transistors. He is going to select the width of M2 digitally, program the width of M2. He is going to digitally program the width of M1 as a one-time characterization on a per wafer lot. So this was his original plan. Post silicon, yes. Per wafer, 1 code. This was his plan. The claim, however,
Sorry, sir.
yeah.
Sir, if we remove VDD on the top, sir, then what would be the leakage? Is there would be any leakage? The VDD.
No power supply.
Yes, sir.
No power supply, then there is no leakage, right? Think of your CMOS inverter. All right, always go back to the CMOS inverter, right? PMOS, gate is at VDD, source is at VDD, drain is at ground, then there will be leakage because source to drain voltage is large. Okay, if source to drain voltage is 0, then there is no way current will flow, leakage or not.
Sir, in this case, sir, when there is no VD, then transistor is in off state, na? So you told that in off in cutoff state there is a leakage.
Gate and source are at equal voltage. Drain and source don't have to be at equal voltage.
Okay, sir. There is some potential difference.
Yes, if drain and source are at equal voltage, then it doesn't matter what gate and source are, there will be no current, right? Remember the MOS characteristics. If drain source is 0, then no current flows, right? Wherever you are, as far as VGS is concerned.
Thank you, sir.
So, have I answered your question? So, the plan is that his original plan was that we'll do per wafer characterization. We'll pick one, select one particular part from the wafer, do a factory calibration, and the same factory calibration is going to be applied to all the others. But the claim of the paper, right? The claim of the ISSCC paper is that this was his plan, but when it came to measurements, he found that it was not required. It behaved the same no matter what. We have not been, so when we have done simulations, we have not seen that. We have seen that you do need per wafer calibration. So I don't particularly agree with the claim of the paper, but he's the one who has done the measurements and over across wafer lots. He has done the measurements across wafer lots. I have not measured across different wafers. All right. So this particular paper won the best paper award in ISSCC 2012, I believe. He also has a JSSC paper based on that, and that also is extremely popular. Now, just keep that in mind and look at a few more configurations over here. So I have PMOS, both devices in weak inversion in saturation, right? I can again equate I1, I2. Gate source are shorted. So this device is definitely in weak inversion. If I choose this device as small and this one as big, right? I write out the equations accordingly. I can compute VA, which is the gate to source voltage for PMOS, the top PMOS, right? And it's just a cranking of equations. You will find that this VA is a PTAT voltage, which is proportional only to the ratio of the widths. Here, the two devices are of the same flavor. All right, this is a simple PTAT. Again, one more configuration. NMOS, same flavored devices. Right? This one is big. This one is small. The small device gate to source is equal to 0, which means it's definitely in weak inversion. I can find out this particular voltage, VB, which is the gate to source voltage of the upper NMOS. I can crank it out. I3 is equal to I4, drain current, write the equations, solve, and it happens to be, again, a nice PTAT voltage. All right. So instead of using difference of VBE, can we use one of these PTATs? Right? There is no calibration required. This is straightforward ratio of two widths. It turns out that this is a pretty clean PTAT voltage. I'll show you in the next couple of slides. So this was another work The reference has been hidden by this bar at the bottom. I can't remove it, but anyway, there is you'll get the slides, right? Will they be given the slides?
No, we'll discuss.
Huh? No? Okay. Anyway, so this is one other reference paper, again from the same group. No, it is still there.
Hello, can I ask a question here?
Yes.
In the previous slide, in the initial proposal, you said the PMOS and NMOS should have different
Yes.
whatever. Why it is?
Because otherwise you won't get CTAT and PTAT, the two combinations. Otherwise you'll have only this PTAT.
Okay.
Like over here.
Okay. So you if you want PTAT, you don't need a you can
Yeah, you can have the same flavor. Yeah.
Okay. Thank you very much.
Okay. All right. So based on what you have seen over here, right? If I have PMOS, then the gate to source voltage of the upper PMOS is a PTAT. If I have NMOS, gate to source voltage of the upper NMOS is a PTAT. So this particular concept was used over here in this work. This is also coming out of the Michigan people, right? Dennis Sylvester and Blau. So it's the same, the reference is hidden. This gate to source voltage is a PTAT. So whatever this voltage is, this is Vx plus PTAT. If this is Vx, then this is Vx plus a PTAT. Op amp, right? Op amp is going to make sure that minus and plus, if it's working properly, they are at the same potential, hopefully. This is at Vx, this is at Vx plus a PTAT, and therefore you have got PTAT voltage across this, right? V PTAT divided by R is the current that is being forced through the load. All right. So of course, there are issues over here. If you want to, yeah.
The NMOS configuration here, it is opposite of what is there in the next slide. Like here, the gate is connected to the top and gate is connected to the bottom, right? Both of them are NMOS. Yeah.
This particular node is actually free. This can be anything.
Oh, it's open.
Okay, so let's pause. Just think a little bit. As long as the two currents match, right? The gate voltage doesn't matter.
So it has to be in weak inversion and it has to match basically.
It has to be in weak inversion. It has to match. That's all. So that's why I've put a dashed line over there that you may connect it to VDD. You need not. It can be any voltage. Yeah.
Yeah. How about the bulk connections? If both PMOSs are there or both NMOSs are there, right? Will the
yeah, bulk connections is a problem.
How is the dependency?
Bulk connection is a problem. You have to match the bulks.
Okay. And how about the VDD variation?
VDD should not matter over here.
Okay.
As long as there is enough VDS to drive the current in the first place.
But the current varies with VDD variation, right?
So beyond a point, current doesn't vary with VDD. Yeah, it's very, very, very low variation with VDD in weak inversion. All right. So body effect is there, right? We'll have to work with the body effect to, you have to deal with the body effect, basically. All right. This is another work. This is our work that came out of our lab. So what we did was we used the same concept over here. We have explicitly shown the bodies over here. Body and source are connected, and PMOS is being used in this particular case. And what we have over here is a small feedback loop to make sure that this current is indeed equal to this current. That will make sure that this is the desired voltage reference. And then, I'm sorry, that will make sure that A is at a PTAT voltage. This particular gate voltage is PTAT, right? Because only when this gate is a PTAT voltage does B node stabilize. Is this okay? And what we can do over here is we can have a very small PTAT slope. This is a sub nanoampere PTAT slope. Over process corners, of course, it varies. In simulation, it does vary over process corner. Unfortunately, in measurements, I don't know because we only get one wafer to measure. We don't get multiple lots. All right, I'll speed up a little bit. So with this particular PTAT core, it's a very low current PTAT core. You can use this and add it to the CTAT BJT VBE and develop a band gap. So what we did over here is instead of, so this is our PTAT, VPTAT, proportional current, VPTAT by R. That is being added to VE by 3 over here in this particular case. All right, so I'll skip all these details in the interest of time. And we measured it. It was not bad. Maximum measured deviation of 4 millivolts across 150 degrees Celsius. Line regulation as well as current consumption. So we have a close to a nanoampere current consumption and 0.6 volts power supply. It still had pretty decent line regulation at 0.6 volts. 1 nanowatt of power consumption at 0.7 volts. Of course, the current builds up with temperature. Why is that? The current becomes, it's exponentially related to temperature because the entire premise is leakage, right? The leakage part, the current builds up exponentially with temperature. So that is expected. This is okay. I'll skip all of this. All right. Now, some interesting other allied ideas, power management circuits. One is something called an under voltage lockout circuit. Sometimes you want a power management circuit that locks out the load if VDD is not enough. Okay, so we are not really talking about band gaps anymore. We are moving a little bit forwards, right? This could be an application of a band gap. You could think of it as an application, right? I want to make a circuit. So I have a power management circuit. Power management circuit has a load. There is a load over here outside somewhere. All right. And the load has a switch on it going to VDD. I want to disable the load if VDD is not large enough. And I want to enable the load when VDD is good. This is the application. So we'll have this band gap reference, right? Compare it. But remember, all of this has to run even when VDD is not good. That's the challenge over here. Even when VDD is not good, you need all of this to run. So you have a band gap reference. You want to compare your band gap reference against a fraction of VDD, right? And then decide whether to switch on the voltage or not. But you also want to build in some hysteresis into this, because otherwise the load is going to keep switching on and off, on and off, on and off. You don't want that to happen, right? You want this fraction to be large while it is booting up, and you want the fraction to be a little smaller than that after it has booted up. Okay, so that's why there is a logic block over here that controls the value of the resistor. So this is an application of a band gap, and we have to do this across temperature, and we have to do this even when VDD is poor. So going back again, yeah.
So when you talk about the PMIC, power management IC, it has lots of other modules such as LDO. So how do we integrate this band gap reference along with them?
We'll see, LDO is just another application, right? We'll see, right? This is, I'm just picking up one particular application, an under voltage lockout circuit. And we have used again the 2 transistor voltage reference, but I have gone one step further. I have added a second one over here, a third transistor over here. And if these two are the same, then this is also going to be VREF, this is also going to be VREF. So you are actually going to get 2 VREF over here. Just a modification. And you'll get a floating voltage reference in this case. What we further did was we divided up this floating voltage reference, right? We took a fraction, and now I can logically choose whichth fraction I'm going to take, compare against. Remember, we need to have 2 comparison points for this logic, for this comparator. We need to have 2 points, one higher voltage, one lower voltage. While booting up, it has to be a higher voltage. While coming down, it has to be a lower voltage. So for that, I've made all these fractions, right? Maybe I'll pick from here and maybe here, right? For the 2 different cases. So all of these corrupt, right? The reference. The current through all of this is going to damage the value of the reference. So you'll have to be careful over there. It's also going to be very noisy for that matter. So a lot of capacitance has to be added to reduce the amount of noise in all of these nodes. Resolution, I don't know. Just a few will do. All right. So that's one part of the strategy. The other part of the strategy is I need a comparator that works. This op-amp, it's not really an op-amp, it's a comparator over here. I need a comparator that works even when the power is not good. And for that also, I can go back to my weak inversion circuits, extremely low power comparator. So what I have over here is the same 2 transistor circuit. If this particular voltage is equal to VREF, then these 2 currents are equal. I1 is equal to I2 if this voltage is VREF. If this voltage is a little more than VREF, then I1 is going to be lesser. If this voltage is less than VREF, then I1 is going to be more than I2, and this is going to trip. All right, it's going to trip one way or the other, depending on So it's like a built-in comparator against VREF, the band gap voltage. And then finally, we have this under voltage lockout, right? This was, we designed this for a few picoamperes, as in no power at all. It was very tough to measure the power. It worked very well in the lab. This is my comparator. There is some selection logic over here to control which switch to select, right, coming out of the reference. And beyond that, it's just a trail of inverters that sharpens the signal, whether it goes high or low. Time is up. We have 5 more minutes. Yeah.
10 minutes also.
Okay, 5. All right. So last few slides. Oh, this is measured results, high to low trip point, and so on. These are all measured results of the chip. You have a lot of trimming possibilities with this. You know, one-time trim, per wafer trim, all of that can be done. All right. Now, another small idea that we developed in our lab was an extension, once again, an extension of this 2-transistor voltage reference. What we did was we added a third device. So this is my 2-transistor reference. I've added a third device, which is a power MOSFET. Let's call it a power MOSFET. Okay. And put it in feedback. So this is a source follower. And we have put this in feedback. Let's say beta is 1. Let's say this is a wire. So it's directly in feedback. What we have now is a voltage regulator with a built-in band gap with 3 transistors. We tested this. It works from 0 to 10 milliamperes, provided you choose that M3 to be large enough. It doesn't require any compensation. It's fundamentally stable because there's only one pole in the system. So no further compensation is required, no dominant pole compensation, no Miller compensation. It works for any load capacitance. And all you have to do is size M3 to provide the requisite current. So we made it as large to provide 10 milliamperes. That's fine. You can have a bigger one to provide as much current as you want in the load. So what's happening over here? This node is stable only when this node is equal to VREF, right? Why? Because I1 and I2 are required to be equal. I1 and I2 are going to be equal only when VGS of M2 is equal to VREF, right? That's what you got from all of the maths earlier. Fine. If this is equal to VREF, then Vout is equal to VREF. As straightforward as that. Sorry, can't hear you. VT equal to 0. It's a power MOSFET, something that provides that can provide a lot of current. You can make it as big as you want. Native is good.
It's a traditional
leakage from the gate. Right. You gate leakage. I mean, that's a different story. Yeah.
M3 size will be.
CC is for noise.
will be a M3 will be a like a traditional LDO switch size, something like that.
Size?
Yes.
No, M1 and M2 have to be adjusted. The size of M1 and M2 need to be adjusted as per the calculations earlier.
Hi, sir. What about the PSRR?
Right?
What about the PSRR of this architecture?
PSRR is bad.
Bad.
PSRR is just one transistor,
Yes,
right?
yeah, 1/GM is there.
Yeah. So PSRR, if there's only one device, then you basically get PSRR worth one device.
Okay.
M1 and M2 need to be sized such that you get a VREF, a reference voltage. M3 can be sized as large as you want depending on the load current you desire. So that's the principle. You can also have programmability. For example, if I make beta a resistive ratio, R1, R2 voltage divider, right? If I provide R1, R2 voltage division in this beta network, then I can make V out a multiple of that VREF. That's also possible.
Yeah. Hello. What about the reliability of the M1? It is the PMOS devices, and VREF is something we can say it is a full floating voltage. So if our supply is 3 volt and M1 is 1.8 volt devices, so is there any chances?
You need to make sure your supply is within the bounds of the reliability. Yeah.
What his question is, the gate of M3, how much swing you will get so that M1 is always in sub-threshold?
You won't get swing. So we are talking about DC over here. Okay, let's talk only about DC. Yeah, this particular circuit will behave badly with transients. It will behave badly with frequency, right? For all those, you have to add more to it. It won't be as simple as 3 transistors, but it can be done. This is just to seed an idea forward. Yeah, this is basically the control system model. Control system model basically tells you that G of S over here is a perfect integrator. So I1 and I2 have to be equal. And therefore, you will get an output voltage that is VREF or 1 by beta times VREF. All right. So with this, I'll stop. We are on time. And yeah.
Couple of questions like regarding the PTAT circuit where both both the transistors are same. So I'm just wondering, how do we control the slope and how the slope is compared to a normal PTAT slope? Is it comparable? Okay, it's just by sizing the W. But when we are in weak inversion, the sizing is independent of the current. That's where I'm.
Sizing is not independent of
the current. Like it's
more the width, more the leakage. Wider will have more leakage.
But I guess in a different form of circuits, I mean, I've seen that the GM is constant. It's like irrespective of the size for a weak inversion circuits.
No. You have your equation, weak inversion equation, which has W. This is your equation, weak inversion. W is there. Size matters, right? I mean, conceptually, if I have a very narrow channel, if I have a very narrow path, then current will be less. If I have a wider path, then current will be more. I mean,
we are talking about leakage current, right? We are not.
Leakage is VDS.
It's independent of the actual width.
No, leakage is VDS.
Yeah, leakage is
VDS.
Yeah,
Forget VGS.
It's a constant because VREF. We are talking about
no
VREF voltage.
No, VDS, think of VDS, right? If I increase VDS, it's like a resistor, right? And the resistor depends on how wide the channel is. If I have 2 transistors, then the current will double. If I put two MOSFETs, then I'll have double the leakage. So that tells you that if I double the width, then the leakage will double.
So now we're saying that the slope is directly a function of the ratio of the sizes of the devices. So
log of that.
We can control it however we want.
You can control it however you want. Yeah.
Okay, that's interesting. Okay. And the band gap reference voltage is also in subthreshold, right? I mean, that's what it's about 200 odd volts. So we will have a limitation. If we have to use this band gap reference voltage somewhere outside, probably we have to use a PMOS. NMOS base is not possible because designing any subthreshold circuits in the application may not be as easy as
correct.
Right? Okay. Thank you.
Yeah. We are talking about weak inversion because this equation for the MOSFET looks like a BJT only in weak inversion. And yes, this equation is really good. It has, by now it has been quite well modeled and the foundries match with this model quite well. So there are no effects, right? There is a lot of noise, but noise is something that you can filter out with appropriate amount of capacitance. Yeah, you'll have to program the sizes. You'll have to program the sizes of M1 and M2 so that you get the best performance on a per wafer basis, ideally.
The result might be different than how we ensure that it will work after fabrication.
Sorry?
Suppose here we calculate W1 and W2, then according to our requirement.
No, what is normally done is you'll build. So in simulation, you find this is W1, this is W2. But this is not what you should manufacture. What you should manufacture is, an array of devices, and program on top, program on bottom digitally. This is what you should be laying out, right? And during testing, you figure out what is the number over there, what is the number over here, and set it once and for all. This is called one-time factory calibration.
Okay, okay, thank you.
Okay, thank you.
Thanks, Professor. I think it was very interactive too. Thanks for audience. So it has.
I have some reference slides. Maybe. Yeah. Actually, this. Yeah.
Thanks all. I believe this session is too informative. And I personally had better informed Bandgap today than what I have yesterday. So it has been such an honor to be part of this wonderful event. On behalf of VLSI Design Committee and Silicon Labs, I would like to extend my whole gratitude for our esteemed guests. Sincere thanks to all departments, admin, IT, facilities, volunteers, organizing committee, Venkatesh, who has handled this event throughout. A wide round of applause to all participants here, who has made this event memorable one. especially after pandemic, right? It's a large gathering we could see. So I would like to call upon Venkatesh Narasimhan to conclude this session by presenting mementos to the guests and speak a few words.
Yeah, so sincere thanks to Sauri and Rakesh here. And I mean, unfortunately, all three could not be on in person, but it's absolutely fantastic to see you all in person. In case, okay, you're wondering, the session has been recorded. It might in the future be made available to you. Okay, the VLSI organizing committee will look at that. There will be some conference archives which will be published in the future. So you might have an access to that. And meanwhile, if you do have other questions later on, or you want to interact with Professor Shauri, for example, I'm sure you can write to him. Okay, so thanks everyone. And we would like to have a kind of a small token of appreciation to the speakers today. So, yeah. So, yeah, Shauri. Thanks so much. And I know you'll remember this visit, but still there is something to remind you of it. Yeah, so Rakesh. Thank you so much. And Professor Rajshekhar online, okay, I don't know if you can see us. I don't know where the camera is pointing, but this is for you. We will have it sent to you wherever you are. Thank you.
Thank you very much.
All right, so everyone, we are breaking for lunch. The lunch is here. Feel free to have to seat yourself, and we'll resume. If you are going to be here for the next session, it will start at 1:30. Okay, if you have registered to any of the other tracks, you will have to go to the 14th floor. After you finish lunch here, you can go to the 14th floor if you're registered to the other tracks. Yeah.
Please do reach out to volunteers for any help.